Hello, hello. How's it going, everybody? Hope you're having a wonderful day so far. We are back. We are back. Today is December the 31st, the last day of 2024. Wow. We have officially made it to the end of 2024. It's been a good year. Lots of stuff we improved on and learned upon. How are you guys doing? Welcome, welcome. Let me go ahead and queue up a message to the Discord saying that we are live. All right. All right, awesome. I think we're good to go here. Oh, Airsick Titan, hello, hello. Um, Christy, welcome in. We had some people waiting in here before I got started. Awesome. Appreciate you guys joining with me here. Mahan, welcome in. Happy New Year to you guys. How's it going? How's your guys' New Year treating you? Anybody do anything fun over the New Year? Hopefully you guys aren't are a little coherent today for the stream. I haven't been partying too much. How's it going, you guys? Welcome, welcome. John Davila, welcome. Davila, welcome. I appreciate you. How you doing? Script Serpent, Serpent said, made a tic-tac-toe game. Awesome. That's so cool. You have to put a demo into the Discord. Immoral Rover, hello. It's so awesome to hear from you. How you going? How's it doing? Happy New Year to you guys. Appreciate you guys joining me. All right, yeah, yeah, sure. Um, share your guys's projects. Yeah, let's see them. Awesome. Okay. So yesterday we left off on positional lists, and I'm not gonna lie, you guys, I was kind of struggling with wrapping my head around these. I just was, it was pretty, it started to get really complex here really fast, and it just started getting really elaborate. So I think we need to do a better job of taking notes on the positional list and then sorting a positional list in 7.5, and then we are done with the chapter 7, and we can move on and do some practice problems in into 7.8 here. So we have 7.6, 4, 5, 6, and 7, and then we are done with this chapter. Okay. Can someone sacrifice so I know if I could send links in here? I don't think YouTube lets you send links in the chat. But yeah, for sure in the Discord, throw some links in there if you guys are wanting to share some stuff. Okay, so let's go back here and let's look about the positional list ADT. Okay. The abstract data types that we have considered thus far, namely stacks, queues, and double-ended queues, only update operations that occur at one end of the sequence or the other. We wish to have a more general abstraction. For example, although we motivated the FIFO semantics, first in, first out semantics of a queue, and a model for customers who are waiting to speak with a customer service rep, or fans who are waiting in line to buy tickets at a show. The queue ADT is too limiting. What if a waiting customer decides to hang up before reaching the front of the customer service queue? Or what if someone is waiting in line to buy tickets allows a friend to cut in line at that position? We would like to design an abstract data type that provides a user a way to refer to elements anywhere in the sequence and perform arbitrary insertions and deletions. When working with array-based sequences such as a Python list, integer indices provide an excellent means for describing the location of an element, or the location at which an insertion or deletion should take place. However, numeric indices are not good choices for describing positions within a linked list because we cannot efficiently access an entry knowing only its index. Finding an element at a given index within a linked list requires traversing the linked list incrementally from its beginning or end, counting elements as we go. Furthermore, indices are not a good abstraction for deciding describing a local position in some applications. Because the index of an entry changes over time due to insertions or deletions that happen earlier in the sequence, right? For example, it may not be convenient to describe the location of a person waiting in line by knowing precisely how far away that person is from the front. We prefer an abstraction as characterized in figure 7.14, in which there is some other means for describing a position, right? When we wish to model those situations, such as when an identified person leaves the line before reaching the front, or which a new person is added to the line immediately behind another identified person. Okay. As another example, a text document can be viewed as a long sequence of characters. A word processor uses the abstraction of a cursor to describe a position within the document without explicit use of an integer index, allowing operations such as delete the character at the cursor or insert a new character just after the cursor. Furthermore, we may be able to refer to an inherent position within a document, such as the beginning of a particular section, without relying on a character index or even a section number. That may change as the document evolves. Interesting. All right, we got some chats in here. Hello, everybody. Welcome in today. How you guys doing? I hope you guys are having a wonderful day so far. Thank you so much for joining me here on this New Year's Eve. For me, it's still December 31st at 7:35 p.m. I'm on the West Coast of the United States, so for those they are technically in the future, which is really cool to think about. You guys are already in 2025, so you guys are in the new year. So super cool and super awesome that you guys are here with me today. I appreciate you guys joining me. Web Dino Developer says Happy New Year. Welcome, dude. I appreciate you coming in. It's awesome to hear from you. I haven't read that name in chat before. It's awesome that you came and joined us this evening. Feel free to follow along if you're enjoying hanging out with me here. Nolan, I want to try your Connect 4. Awesome, yeah. You guys look like you're sharing some projects here in the Discord. So if you guys are new, please join the Discord linked in the description below, where we share all of our resources offline, from the PDFs that we're studying to our individual notes, kind of providing a roadmap for my learning as I am going forward. And also looks like some other people are sharing their personal projects in the Discord as well. And so yeah, go ahead and check that out if you want to collaborate with everybody offline. Looks like my connection on my stream might be kind of chopping up in and out here. Looks like I'm dropping a couple frames, so bear with me if it gets a little bit choppy here. I'm gonna try to, it should kind of work itself out here. All right. Not only Dev, hey, how you doing? Happy New Year to you. I appreciate you coming in. Web Dino says it's 10:35 p.m. over here. Oh, so not yet the new year, just like me. All right, are you over on the East Coast then? You're 3 hours ahead. Okay, so let's ask. Give me a simple def for a positional list ADT. Okay, a positional list ADT. Here we go. Positional ADT is a list-like data structure that allows elements to be accessed, inserted, or removed based on their position while maintaining relationships between adjacent elements / nodes. It includes a concept of positions, which act as markers or reference to elements within the list, rather than using numerical indices. A positional list ADT supports operations such as first, returning the first position, last, returning the last, before P, returning the position with the element before, after P, returning the element, add first, insert a new element at the beginning, add last, add before, add after, delete, and replace. The abstraction provides flexibility for operations that rely on relative positioning, such as maintaining sequences. So how does positions differ from index places? Right. Positions in ADT, positional ADT, differ from index-based positions in the following ways. Abstract versus numeric. Positions are abstract markers or references to elements in the list. They do not correspond to fixed numeric values. Indices are numeric and correspond to the absolute position of an element in a sequential data structure like an array. For example, a position is like a bookmark pointing to an element. An index is like a specific page in a book. Ah, okay. So, um, we'll go like this to here, examples, 1, 2, and we'll come here and we'll say index is versus positions, right? So positions are abstract markers or references to elements in the list. They do not correspond to fixed numeric values. Indices are numeric and correspond to the absolute position of an element Okay, so we'll do like here and say position is like a bookmark in a book, whereas a index is like a page number of a book. Cool. All right. WebDino developer says we are in Michigan. Ah, cool. John Davila says CS50 class tomorrow. Yeah. So hopefully, for those that are unaware, we're going to be starting up the Harvard CS50X course, which is their introductory computer science course. We're going to be starting the revamped 2025 version starting tomorrow on January 1st, 2025. So I think tomorrow we will go ahead and start week 0 and watch a lecture together and maybe take a stab at the problem sets. So yeah, I'll join the Discord if you guys want some more information. I'll be posting probably tonight or tomorrow morning just some more information about how to sign up and then when we're going to be officially doing the watch along. I'm just waiting for them to kind of launch that course. I've been keeping tabs on it. It hasn't been officially launched yet. So dynamic versus fixed. In a positional list, positions are dynamic and remain valid even if elements are added or removed elsewhere in the list. Position provided they don't directly affect the position. In an index-based list, indices are fixed relative to the start of the list, but they can shift if elements are added or removed. For example, inserting an item at index 0 shifts all subsequent indices. Relative navigation. Positions allow for relative navigation via operations like before P and after P to access adjacent elements. With indices, you must compute relative positions by adding or subtracting 1. Implementation context. Positions are often used in linked list implementations where elements are stored non-contiguously in memory. They abstract away the underlying links and provide a way to work with elements as if they were part of a continuous structure. Indices are used in array-based implementations where elements are stored contiguously in memory, making random access via numeric indices efficient. Positional lists add element X before position P. You don't need to know the numerical location, just the reference P. Add element X before index 5. You must calculate the numerical index and ensure you update indices for subsequent elements. So I'm not sure though, like how do you know what reference P is? How do you know what Um, reference P is if adding element X before P. Um, in positional list ADT, the reference P is a position object provided by the list when interacting with elements. Here's how it works. Each position on the list is represented by a position object, which acts as a reference or marker for a specific element. The position object typically stores a reference to the node and in the linked list and information about the list that owns it. How to get the position. The position object P is returned by certain operations in the positional list, such as first, last, before P, and after P. So list, we have a positional list here. P is equal to list.add first, quote A, add as the first element. Oh, because you can physically save the position as P as a variable is what it means. So you have the physical location of add first, add after the position. When you add before P, the list internally uses the position object P to locate the corresponding node in the underlying structure. Okay. Okay, interesting. What time zone? I'm on the West Coast PST, so it'll probably be somewhere. I don't have work tomorrow, so for those that don't know, I work a 9 to 5 job as a formulation chemist, and tomorrow I do have the day off for the new year, so we will probably do a little bit of an earlier stream tomorrow and go over the CS50X course. So example would be a cursor in a text document. Another example would be cutting a line, cutting in line, right? Or Q, right? Okay. A node reference as a position. One of the great benefits of a linked list structure is that it is possible to perform O of 1 time insertions and deletions at arbitrary positions of the list as long as we are given a reference to a relevant node of the list. It is therefore very tempting to develop an ADT in which node references serve as a mechanism for describing a position. In fact, our doubly linked base class of section 7.3.1 has methods underscore insert between and delete node that accept node references as parameters. However, such direct use of nodes would violate the object-oriented design principles of abstraction and encapsulation that were introduced in Chapter 2. There are several reasons to prefer that we encapsulate the nodes of a linked list for both our sake and for the benefit of our users of our abstraction. So I want to throw this in there and say, can you explain this? This explanation highlights the importance of encapsulating the details of a linked list implementation when designing a abstract data type. Why over insertions are possible? In a linked list, the key advantage is that you can insert or delete elements in constant time if you have a reference to the relative node. To insert, you update the pointers links to the surrounding nodes. To delete, you bypass the node, removing and adjusting the pointers. So before we have A, which points to A and B, which points to B and C. We insert X after B, which is, okay, got you. Temptation to use nodes references directly. It may seem simple to expose these node references as part of the ADT structure. Users could pass a node directly to operations like insert between and delete node. This would make it possible to leverage O of 1 performance directly. Why this violates object-oriented design principles. Directly exposing nodes goes against two key principles of object-oriented design. A, abstraction. Abstraction means hiding the details of how a structure works internally and exposing only a clean, high-level interface. Nodes are low-level details of a linked list implementation. By exposing nodes, the user of the ADT becomes aware of and dependent on the underlying structure. If the internal representation changes, switching from a linked list to an array-based structure, the exposed node-based interference would no longer work. Encapsulation. Encapsulation means bundling the internal state and behaviors of an object and protecting it from direct external access. Nodes are part of the internal state of the linked list. Exposing nodes allows users to modify the list state directly, bypassing safeguards. For instance, a user might inadvertently break the list by altering a node's pointers incorrectly. Encapsulation through position objects. Instead of exposing nodes, we encapsulate them within position objects. A position object acts as a high-level abstraction that represents an element's location in the list, prevents direct access to the internal structure, maintains consistency and integrity of the linked list by ensuring that operations go through the ADT's method. For example, add before position P element X internally accesses the node corresponding to P and modifies the list safely. The users don't need to know how the list is implemented or worry about breaking its structure. Okay, so all we need to know is a reference to what element we want to add before or after, and then give the element we want to add before or after, rather than iterating over the list, gaining access to each element reference of the list, and then maybe potentially breaking it. So benefits of encapsulation. Flexibility. The internal implementation of the list can be changed without affecting the users of the ADT. For instance, you could switch from the doubly linked list to a circularly linked list without modifying the external interface. Safety. Users cannot accidentally corrupt a list by directly manipulating node references. Simplicity. Users don't need to understand or interact with low-level details of linked list. So example, the doubly linked base. The doubly linked base class provides methods like insert between and delete node, which require node references. These methods are internal utilities, not part of the public interface, are used for higher level methods like add before to ensure the list integrity. Okay, got you. Here we go. Your boy Frosty, thanks so much for coming in. What kind of project are you looking to do? Yeah, so for those that are new and just joining me, in the beginning of my streams, we do learning and increase our learning. So we just passed page 300 here of data structures and algorithms in Python. We are currently focusing solely on Python and teaching ourselves Python for the time being. So we are just kind of we're reading over this book and doing the practice problems at the end of the chapters, and then at the end of my streams or in the back half of my streams we work on our independent projects. And so we work on the small business manager, which can take in inventory items, convert those items into for sale, convert those for sale items into sold, and then obviously generate reports and provide basic business data associated with kind of a sales format. So this is the project that we've been writing live on stream in the back half. So we'll get to that eventually. I appreciate you joining. Same, I'm off work early. I'm off, but working early on my information security classes that start back up next week. I'm taking time for CS50 with y'all. Awesome, that sounds so good, John. I really appreciate that you're interested and wanting to follow along with that with me. It'll be a really good opportunity for us to kind of work together. I know if I'm going to be completing it on stream, you might as well follow along and submit the problems as well and get the credit for it too. You might learn something along the way as well. So I appreciate that. That's awesome. Okay. It will be simpler. Okay, let's keep going here. For these reasons, instead of relying directly on the nodes, we introduce an independent position abstraction to note the location of an element within a list, and then a complete positional list ADT that can encapsulate a doubly linked list. Got you. To provide a general abstraction of a sequence of elements with the ability to identify the location of an element, we identify the positional list ADT as well as simpler position abstract data types to describe a location within a list. A position acts as a marker or a token within the broader positional list. A position P is unaffected by changes elsewhere in a list. The only way in which a position becomes invalid is if an explicit command is used to delete it. A position instance is a simple object supporting only the following methods. Okay, so here we go. um, position instance are simple objects that support um, in the context of the positional list ADT, positions serve as parameters to some methods and return values from other methods. In describing the behaviors of a positional list, we present the accessor methods supported by a list L. Support the following method of here we'll go p.element, which returns the element stored at position p, right? Then we say in the context of positional list ADTs, positions serve as parameters to some methods and as return values from other methods. In describing the behaviors of a positional list, a position list supports the following methods, right? Go here, and then, so one, like that. All right. L dot first, which does returns the position of the first element L. So 2 L dot last, we'll take this guy, put it here like so. Number 3, I'm just going to take all of these like this. Right, like so. 4, we'll take all these, indent them in like so. Here is 5. Length L gives us 6. Iter L 7. I'll say this here. 1, 2. Whoops, not the position of the element. This is going to be 2 here, 3 here, 4 here, 5 here, and 6 here. Okay. Cool. This is underscore empty. Awesome. So we have all of these methods here that can be used for positional lists. Okay. Note well that the first and last methods of the positional list ADT return the associated positions, not the elements. This is in contrast to the corresponding first and last methods of the dec ADT. The first element of the positional list can be determined by subsequently invoking the element method on the position L.first.element. The advantage of receiving a position as a return value is that we can use a position to navigate the list. For example, the following code fragment prints all elements of a positional list named data. So we have cursor equals data.first. So this is a reference to the first position, while cursor is not none, meaning that we have data in our position, we want to print cursor.element, and cursor is equal to data after cursor. So what is the after function or after method? Add after. This code relies on the stated convention that the none object is returned when after is called upon the last position. That return value is clearly distinguishable from any legitimate position. The positional list ADT similarly indicates that the none value is returned when the before method is invoked at the front of the list, or when first or last methods are called upon an empty list. Therefore, the above code fragment works correctly even if the data list is empty. Because the ADT includes support for Python's iter function, users may rely on the traditional for loop syntax for such a forward traversal of a list named data. For element in data, print e. Okay. More general navigation and update methods of positional list ADT are shown in the following example. So l.add last at position p so add last return value of p returns the position. So add last, insert a new element e at the back of the list, returning the position of the new element. Okay, so returns the position that A is in. First, references the position that 8 is in. Add after position P that was given is going to add the 5 after P with it's going to return a value of Q, the position that 5 is in. L before Q is going to return position P. List add before Q is going to put the 3 in there with R. Okay. Interesting. Doubly linked list implementation. In this section, we present a complete implementation of a positional list class using a doubly linked list that satisfies the following important propositions. Prop 7.2, each method of the positional list ADT runs in worst case O of 1 time when implemented with the doubly linked list. We rely on the doubly linked list base class from section 7.3.1 for our low-level representation. The primary responsibility of our new class is to provide a public interface in accordance with the positional list ADT. We begin our class definition in code fragment 7.14 with the definition of the public position class nested within our positional list class. Position instances will be used to represent the locations of elements within the list. Our previous positional list methods may end up creating redundant position instances that reference the same underlying node. For example, when first and last are the same for that reason. For that reason, our position class defines the dunder equivalency and dunder NE special methods so that a test such as P is equal to Q evaluates a true and two positions refer to the same node. Validating positions. Each time a method of the positional list class accepts a position as a parameter, we want to verify that the position is valid, and if so, to determine that the underlying node associated with the position. This functionality is implemented by a non-public method named _validate. Internally, a position maintains a reference to the associated node of the linked list, and also a reference to the list instance that contains the specified node. With the container reference, we can robustly detect when a caller sends a positional instance that does not belong to the indicated list. We are also able to detect a position instance that belongs to the list, but that refers to a node that is no longer part of the list. Recall that the delete node of the base class sets the previous and next references of the deleted node to none, which can recognize that condition to detect an appreciated node. To the access method, access and update methods. The access and methods of the positional list class are given in code fragment 7.15, and the update methods are given in code fragment 7.16. All of these methods trivially adapt the underlying doubly linked list implementation to support the public interface of the positional list ADT. Those methods rely on the validate utility to, quote, unwrap any position that is sent. They also rely on a make position utility to wrap nodes as position instances to return to the user, making sure never to return a position reference as a sentinel. For convenience, we have overridden the inherited insert between utility methods so that our returns a position associated with the newly created node, whereas the inherited version returns the node itself. So we have a positional list class that takes in the doubly linked base class. We have a nested position class. When initialized, it takes in self, container, and node. Container is equal to container, and node is equal to node. So this is just the container is the position itself, I guess. So element, we return the node.element, okay. If we call element on it. Under EQ, return true with the position representing it at the same location. Return the type of other is type self and return type other provided is type self and other node is self.node. So type of other is type of self, and other underscore node is self.node. Okay, so if these are the same node, return true. Under NE, self other returns true if other does not represent the same location. Return not self equals other, opposite of EQ. And then we have the validate, which takes in if self and a position. So return the position's node and raise appropriate error if invalid. If not is instance p and self.position. If p container is not self, okay, let's keep moving here. We definitely need to get some examples with this. Okay, 7.5. Sorting a positional list. In section 5.5.2, we introduced the insertion sort algorithm in the context of an array-based sequence. In this sequence, we developed an implementation that operates on a positional list. In this section, we develop an implementation that operates on a positional list, relying on the same high-level algorithm in which elements is placed relative to a growing collection of previously stored elements. We maintain a variable named marker that represents the rightmost position of the current sorted portion of a list. We maintain a variable called marker that represents the rightmost portion of the current stored portion of a list. During each pass, we consider the portion just past the marker as the pivot, and consider where the pivot's elements belongs relative to the sorted portion. We use another variable named walk to move leftward and from the marker as long as there remains a preceding element with value larger than the pivots. A typical configuration of these variables is diagrammed in figure 7.15. A Python implementation of this strategy is given in code fragment 7.17. So, overview of one step of insertion sort algorithm. The shaded elements, those up to and including marker, have already been sorted. In this step, the pivot's element should be relocated immediately before the walk position. So we def insertion sort L. If the length of the list is greater than 1, meaning that we have more than one element in the list, we are going to set marker equal to the reference to the first position. While marker does not equal the reference to the last position, pivot is going to be the list after the marker, while value, and then we set value equal to pivot dot element. Pivot is equal to the pivot point. All right. I wanted to break down this. Break this down, please. This code implements insertion sort for a positional list, a data structure that provides the ability to manipulate elements on their positions, add, remove, or access elements relative to others. Here's a step-by-step breakdown. A doubly positional list. A doubly linked list where elements has a position node associated with it. Functions like list.first, list.last, list.after position, and list.before position let you navigate between positions. Insertion sort. A sorting algorithm that builds a sorted portion of the list element by element. At each step, it takes the next unsorted element, pivot, and inserts it into the correct position in the sorted portion. So, explanation of the code. Lines 1 through 3, we have initial check. If the list has one or no elements, it's already sorting the algorithm ends, right? Else, we're going to set marker, initialize the marker is set to the first position in the list. The marker keeps track of the last position in the sorted portion of the list. Iterate through the list. While marker does not equal last position, the loop continues until the marker reaches the last position in the list. Pivot. So pivot refers to the position after the marker, which is the first element of the unsorted portion. Value stores the element at the pivot for comparison. Okay, value is just the value of the pivot point. In lines 8 through 9, pivot already in the correct position. If value is greater than marker.element, meaning that the value of the pivot point or the next value is greater than the previous one, meaning that it's already sorted, we set marker is equal to pivot to move to the next element. If the pivot point's value is greater than the marker, the pivot is already in the correct position. Simply move the marker forward to indicate the pivot is in the sorted position. Lines 10 through 13, case 2. Else, we set walk equal to marker, while walk does not equal the list.first and list.before walk.element is greater than value. If the pivot's value is smaller than the marker's value, it needs to be moved leftward to its correct position. Walk is used to move backward, leftward through the sorted position of the list. Walk reaches, okay. Interesting. Okay. We definitely need some practice with this. 7.6 case study. The positional list ADT is useful in a number of settings. For example, a program that simulates a game of cards could model each person's hand as a positional list. Since most people keep cards of the same suit together, inserting and removing cards from a person's hand can be implemented using the method of the positional list ADT, while the positions being determined by a natural order of the suits. Likewise, a simple text editor embeds the notion of a positional insertion and deletion, since such editors typically perform all updates relative to a cursor, which represents the current position in the list of characters of text being edited. In this section, we consider maintaining a collection of elements while keeping track of the number of times each element is accessed. Keeping such access counts allows us to know which elements are the most popular. Examples of such scenarios include a web browser that keeps track of users' most accessed URLs, or a music collection that maintains a list of the most frequently played songs for the user. We model this with a new favorites list ADT that supports the length and is empty method, um, as well as the following. Access E accesses element E, incrementing its access count and adding it to the favorites list. Remove elements E from the favorites list if present, and top K returns an iteration of the K most accessed elements. Like top 3 elements. Okay, cool. Using a sorted list. Our first approach for managing a list of favorites is to store elements in a linked list, keeping them in non-increasing order of access counts. We access or remove an element by searching the list from the most frequently accessed to the least frequently accessed. Reporting the top K most accessed elements is easy as they are the first K entries of the list. To maintain the invariant that elements are stored in non-increasing order of the access counts, we must consider how a single access operation may affect the order. The accessed elements count increases by 1, and so it may become larger than one or more of its preceding neighbors in the list, thereby violating the invariant. Fortunately, we can reestablish the sorted invariant using a technique similar to a single pass of the insertion sort algorithm, introduced in the previous section. We can perform a backward traversal of the list starting at the position of the element whose access count has increased until we locate a valid position, after which the element can be relocated using the composition pattern. We wish to implement a favorites list by making use of the positional list for storage. If elements of the positional list were simply elements of the favorites list, we would be challenged to maintain access counts and keep the proper count with the associated elements as the contents of the list are reordered. We use a general object-oriented design pattern, the composition pattern, in which we define a simple object that is composed of 2 or more other objects. Specifically, we define a non-public nested class _item that stores the element and its access count as a single instance, and then maintains our favorites list as a positional list of item instances. So the access counts for a user's element is embedded alongside it in our representation. Okay, this is just a lot of FUD. We need to keep moving on and get some practice here. Ugh, so much stuff. Just keeps going. So annoying. Ugh, come on. Using a list to move forward to front, move to front heuristic. Ugh, this is, I'm really like not wanting to continue this. This is so annoying. This is getting annoying, you guys. I'm not really enjoying learning about linked lists here. This is taking like kind of the fun out of it, if I'm being honest. Let's keep moving here. 7.7, linked base versus array based sequences. We close this chapter by reflecting on the relative pros and cons of array-based and linked-based data structures that have been introduced thus far. The dichotomy between these approaches presents a common design decision when choosing an appropriate implementation of a data structure. There is not a one-size-fits-all solution, so as each offers distinct advantages and disadvantages. Advantages of array-based sequence. Arrays provide O of 1 time access to an element based on an integer index. The ability to access the kth element of any k in 0, 1 time is a hallmark advantage of arrays. In contrast, locating the kth element in a linked list requires O of k time to traverse the list from the beginning, or possibly O of n minus k time if traversing backward from the end of a doubly linked list. Operations with equivalent asymptotic bounds typically run a constant factor more efficiently with an array-based structure versus a linked structure. As an example, consider the typical NQ operation for a queue, ignoring the issue of resizing an array. This operation for the array class involves an arithmetic calculation arithmetic calculation of the new index, an increment of an integer, and storing a reference to the element in the array. In contrast, the process for a linked queue requires the instantiation of a node, appropriate linking of nodes, and an increment of an integer. While this operation completes in O of 1 time in either model, the actual number of CPU operations will be more in the linked version, especially given the instantiation of the new node. Array-based representations typically use proportionally less memory than linked structures. This advantage may seem counterintuitive, especially given that the length of a dynamic array may be longer than the number of elements that it stores. Both array-based lists and the linked list are referential structures, so the primary memory for storing the actual objects that are elements in this is the same for either structure. What differs is the auxiliary amounts of memory that are used by the two structures. For an array-based counter or container of n elements, a typical worst case may be that a recently resized dynamic array has allocated memory for 2n object references. With linked lists, memory must be devoted not only to store a reference to each contained object, but also explicit references that link the nodes. So a singly linked list of length n already requires 2n references, an element reference, and an x reference for each node. With a doubly linked list, there are 3n references. Okay. Advantages of a linked-based sequence. Hey, Ali Daiwan, I appreciate you coming in and leaving a message for me here. Thank you so much. It says, why did you choose reading instead of decode? I just entered the stream. Sorry if this has already been answered. No, this is a perfectly great question. I honestly don't really have an answer for you. I just, I think you have to kind of, I think you have to pay for neat code, so it was just a free option was reading out of the book. Now, I will say that we are probably getting to the point where we need to start maybe actually practicing some neat code or leak code problems to help further solidify this knowledge. We do practice problems at the end of the chapters, but at this point we can probably start to warm up with maybe some leak code problems to help kind of introduce these concepts into some real applicable questions that we might be asked. So, what do you guys think? Do you guys think we're at a point where we can try to tackle maybe some of the easy leak code problems? Maybe do a couple each stream or something to try to warm up. That'd be kind of cool to help break things up. I'm trying to look for ways to help break up the monotony of the stream. So tomorrow we're going to be starting the Harvard CS50X course on the channel because I know that it can get boring just me reading for a couple of days, but we do need to understand the material and learn it somehow. So I know, but we're almost done here with chapter 7. We'll get into some problems. Advantages of linked-based sequences. Linked-based structures provide worst-case time bounds for their operations. This is in contrast to the amortized bounds associated with the expansions and contractions of the dynamic array. When many individual operations are part of a larger computation and we only care about the total time of that computation, an amortized bound is as good as worst-case bound precisely because it gives a guarantee on the sum of time spent on the individual operations. However, if data structure operations are used in real-time systems that is designed to provide more immediate responses, an operating system, web server, air traffic control system, a long delay caused by a single amortized operation may have an adverse effect. Link-based structures support O of 1 time insertions and deletions at arbitrary positions. The ability to perform a constant time insertion or deletion with the positional list class by using a position to efficiently describe the location of the operation is perhaps the most significant advantage of the linked list. This is in stark contrast to an array-based sequence, ignoring the issue of resizing an array. Inserting or deleting an element from the end of the array based on based list can be done in constant time. However, more general insertions and deletions are expensive. For example, with Python's array-based list class, a call to insert or pop at index k uses O of n minus k plus 1 time because of the loop to shift all subsequent elements. As an example application, consider a text editor that maintains a document as a sequence of characters. Although users often add characters to the end of the document, it's also possible to use the cursor to insert or delete one or more characters at an arbitrary position within the document. If the character sequence were stored in an array-based sequence, such as a Python list, each such edit operation may require linearly many characters to be shifted, leading to O of n performance for each edit operation. With a linked list representation, an arbitrary edit operation, insertion, or deletion of a character at the cursor can be performed in O1 worst case time, assuming we are given a position that represents the cursor location of the cursor. All right, cool. um, Ali Dewan says, "Got you. Yeah, definitely. That's very cool. I actually synchronistically just learned heavily about linked lists. Oh, awesome. Well, you'll be a great help here. I'm not going to lie, Chapter 7 is probably one of the harder chapters we've had to wrap our heads around, just because it's kind of one of the more code heavy chapters. It gave us, you know, big, long data structures that it wrote here. In the form of class and used a lot of like nesting classes and stuff like that. So this was probably the most code heavy chapter we've had to read so far. So it was a little bit difficult in that aspect. Um, but yes, this brings us to the end of chapter 7. Cool. So we are ready to take a stab at some reinforcement problems. Let's see here. Ali HTS50X is amazing. Def love that course. Yes, we're going to be starting that up tomorrow. Christy asked me, what's your New Year's resolution? Um, I think one of my New Year's resolutions is to hit 1,000 subscribers on the channel. We've been growing really rapidly. You guys have been really awesome in supporting me and showing, positivity and giving me a bunch of support here. It's been great. So hopefully in the near future, we can hit 1,000 subscribers this year in 2025 and keep growing the channel. I'm really, really passionate about the channel right now. It's something that I'm really excited about. Coming on these streams and doing them is really motivating because the channel keeps growing. So as long as you guys are, supporting and enjoying what we're doing, I just want to make sure I'm not being too monotonous with the stream and keep having new subjects come in and so people aren't getting bored. Yeah, Ali Dewan, join my Discord linked below. Exactly, where I have a Discord that I created where I provide all of my study resources from the PDFs I'm reading live on streams to information about the individual courses I'm taking, kind of more of a general roadmap of all the resources that I both am using online and in person. And then also it has the opportunity for others to share their projects, share their personal resources that they're using as well. So join the Discord so we can chat offline and you can get access to all that and also provide your own if you want. Yeah, that sounds great. Yeah, we were just at 500 the other day, so 1,000 is definitely possible. That'd be so crazy. Okay, so should we try some practice problems here? All right, it might be difficult here. R7.1 underscore key dot pi. Okay, so let's try a few of these. And then maybe we can try a few leak code problems, maybe the beginner ones, and see if we can, solve a couple of them. I wouldn't mind doing that. That sounds pretty fun. Anyone have any problems that they'd like to suggest that we can maybe take a stab at and try? So far, we've learned about time complexities. We've learned about array-based sequences. We've learned about stacks, queues, and decks, and we've learned about linked lists so far. So we haven't gone too deep into things, but we are starting to make some strides here into some more challenging topics into DSA as a whole. So keep that in mind if you have any suggestions for problems that we can try. Okay, given algorithm for finding the second to last node in a singly linked list, in which the last node is indicated by a next reference of none. Okay. Now, here we go. All right. William, thanks so much for coming in, William. It's awesome to hear from you. I appreciate you leaving a message and joining the stream. Even in New Year's Eve, yes, New Year's Eve, we're keeping the streak and the stream going. Have you done reversed linked lists? No, I haven't. So this is after reading chapter 7 here, this is my first ever introduction into linked lists. And so I'm a beginner programmer. I've been teaching myself for just the past 6 months. So I'm not too far into things. I started with CS50P where I completed that course over this past summer, and then I am working on just independently reading books and teaching myself through various online resources, and then also using the stream as resources through you guys as the stream as well. Um, but this was my first ever introduction to linked lists, so I'm not that great so far. Um, Honestly, I don't even really know where to go to solve this problem here. So if we were to give an algorithm for finding the second to last node in a singly linked list. Okay, so let's go back up to our singly linked list here. Doubly, circularly, and singly. Okay, singly linked list here. So given algorithm for finding the second to last node in a singly linked list in which the last node is indicated by a next reference of none. Okay, so if we're in a singly linked list, we have to traverse down the entire list to find the last value, right? We can't go back up the list. We could use we couldn't use a header or trailer because we would just need to call a return of the value that is hmm um have you ever done release or merged two sorted lists? Def check out those leak code problems. They're great for beginners. I'm self-taught as well, but I'm more experienced. But hey, we'll all start somewhere. Awesome, yeah. Okay, cool. So how can we go about solving this one? So we know that we have to traverse down the entire linked list. So if this is our singly linked list, we want to return the the element that is at the second to last position. So we have to physically traverse from the head down to the hmm, down to the tail and go one back from the tail. But if we reach the tail, we can't go one back from the tail because we don't have a previous. This is not a doubly linked list, right? So add last would take a newest, create a new node. Newest.next is equal to none. List.tail.next is equal to newest. No, so how could we return the second to the last node in a singly linked list in which the last node is indicated by next reference? Okay, so use a temporary value. So maybe we can use a temporary value to house more than one node to traverse down. Um, hmm. I would get a piece of paper and write out what the code is doing to each node. Okay, let's try that. Let's pull out our whiteboard here. Okay, so we have node A. Right, we have this right here. We have node A here. It's going to traverse down to node B. which traverses down to node C. Node C is our tail, right? And we want to return one back. So we need to traverse down until we detect that this reference value is equal to none. No, because this reference value is not equal to none, it's equal to C, which then would be equal to none. Right, because this one is going to come here and equal to none. Right? So if we have, so while I just don't even know really where to start. So would take in anyone have any idea of where to even start? So this will detect our tail. So give an algorithm for finding the second to last node in a singly linked list in which the last node is indicated by a reference to none. So if we say def second to last node is equal to, we're going to take in some positional list, right? We're going to take in some positional list. So we'll say if L dot head is none, right? Raise so if so we have to start from the head. Head is just a placeholder for each node. Each node is a head, yeah. So if head is equal to none, the list is empty. We're going to raise value error as E, or whatever. What do we say? Whatever, we'll just pass here. So else, right, meaning that we have I don't even know. See, I don't really understand linked lists that well. So I just need to iterate through, but I'm not iterating through. So what can we do here? If can we do a simpler problem of returning the last node? Okay, we can try that. So maybe we should try to return the last node first. So let's try to do that one first. Okay, so let's try to do um, so should we second to last node? Okay, so that's what I was thinking. So we have to either iterate or recurse down, right? So that's what I was about to say. So if we call second to last node, what we want to do is if L head is equal to none, meaning that dot next is none, we're going to right. If the head next is none, we're going to return L dot head. Else, we're going to recursively call second to last node on the L dot next. So that's going to return the last value. Hey Mohit, thanks so much for the kind words. Appreciate you coming in. Thanks so much. I appreciate you. That's awesome. Yeah, Mo, this is literally what I've been looking for weeks. Oh, awesome, you guys. Yeah, so my whole goal with this stream was when I was first learning Python and first trying to find resources was that um, every type of stream that I clicked on was an already graduated or about to graduate computer science student or was a professional already in the field. And so what they were working on was pretty advanced and pretty far above my level in terms of being able to pick things up. I was able to kind of understand what was going on, but I wasn't really able to actually learn anything just because there was such a knowledge gap between me and this person. And no, and every stream that I came by was either that format. And then when I was looking for videos, every video that I came by was someone that had already been programming for maybe 5 to whatever years and was trying to then convey beginner concepts from the perspective of someone that was already advanced. And there was just that disconnect between the two of us where they would just kind of brush past maybe beginner subjects or beginner topics because they were like assumed or inferred that they were already known. And that just wasn't what I was really looking for. I was wanting those beginner topics to be broken down so that I could build them back up to help build up those more advanced topics. And so I kind of said, you know what if I just rather, I can't teach anything because I'm learning this myself. The whole point of this channel is to not teach. You and me are peers. We are one to one, as if we had booked a study room in the library at our university and we went together and we were working this out as a pair, you and I trying to teach ourselves as a group. So this is no different than us just hanging out back at university, booking a study room in the library, in my opinion, where you and I are peers or classmates learning this together in this kind of format. And I'm providing a kind of a raw beginner's point of view to help those in a similar situation in myself because I found that there wasn't that information being applied, mainly because probably beginners were probably scared to show that there is that kind of that learning curve and that fear aspect where it can be kind of daunting to put yourself out there and show yourself that and be ignorant and say I don't know what's going on but I'm wanting to learn because that opens us the door for people to either kind of make fun of you or whatever or judge you. I really don't care about any of that. I'm pretty confident in myself and what I do. It's my life, and I really don't care what other people say about it because I'm going to live it how I want to live it. So if I look dumb while I'm on this stream, well, I don't really care because that just means that I'm actually learning something, right? No one ever learns something without sounding or looking dumb, in my opinion, unless they already knew it beforehand, right? So you can't learn something without admitting that you didn't know it or in the first place, at least trying to humble yourself and put yourself in that position. So that's the whole goal for the stream. And then I have the Discord that also down linked below, which provides just like a roadmap or all the resources that I'm using. So if you want to see like similar processes or problems or projects that I've done that you can then follow, or a similar kind of roadmap to take if you're learning, yeah, feel free to join the Discord as well. Yeah, I'm a pure mathematician, so I'm teaching myself to code. Exactly. Yeah, yeah. So I'm a biochemist. I work as a formulation chemist for a biotech company. I graduated back in 2021 with a degree in human biology and a minor in chemistry. And I work as a formulation chemist. I'm a scientist too for the past 3 years, and I'm doing this after my 9 to 5 job. So I'm removing all of those external pressures. Like I don't have a test at the end of the semester or a grade I'm getting. I don't have a teacher or professor that I'm trying to impress, or a boss in this. This is all completely independent, and it should be seen as something fun and to do because I'm, challenging myself and I'm improving upon myself and my education. So we're breaking down those walls of competitiveness within, computer science and CS, and or just kind of more hush hush or whatever, and we're just creating a more streamlined, open environment for everybody to come in and enjoy. You've grown so much. I was here like weeks ago, and you're insanely in progress. Congrats, bro. Keep up the work. Yeah. Awesome. Thanks so much. I really appreciate you guys providing that feedback, because sometimes when you're just little by little, chunk by chunk, day by day, it might not seem like you're really growing that fast. But then when you get some retrospect and when you get some perspective, um, when you get some like perspective on the thing and kind of look back, you see, wow, just a couple weeks ago I didn't know anything about time complexity, but now I'm solving problems based on time complexity. I'm doing all this. I'm learning about linked lists here. I'm trying to learn about linked lists. They're pretty difficult here, but um, I really appreciate you guys saying that, because it just helps me to see that perspective. Yeah, we are improving little by little. This is working. This whole system, right? It's a similar method to, I think that there's just that disconnect. A lot of people online get told that, oh, I completed this course in 3 months and I found a job and I became an expert, yada yada yada. When in reality, that's just not true. Probably, it's there's probably a lot of gray area, a lot of lying going on in those videos, and and I wanted to provide more of an authentic approach. And I can't really. I've been streaming for hundreds and hundreds of hours with you guys so far, so it would be pretty hard for me to fake something, streaming this many hours live in front of a camera to you guys. So this is 100% authentic, and the approach to my learning here. So yeah, I appreciate you guys. Uh, Pradik says linked lists are fairly difficult to understand and implement, so please take your time to learn them. Christy says, I really want my permit. Are you talking about like the driver's permit? That's kind of random. But yeah, that's a good goal to have if you want to for 2025. Yeah, Pradik, I'm definitely struggling with linked lists here. They are I'm having a problem implementing them. Okay, so I think I'm gonna go to the almighty orb and say I am trying to solve. And for those that are new, I do use AI to help me like solve these problems, but I will preface the AI to not show me code. We need to use the AI responsibly, right? I don't have a professor here I can go to and talk to, or like a TA or anything like that, like in school. So we can use the AI as like a TA in a way, but we don't want the TA would never just give us answers. It would want us to learn. So we need to preface that. I'm trying to solve a linked list problem and am having trouble figuring out where to start. Here is the problem. We'll copy this up, paste it here, and say, don't show me code, but in words, please help me get started. Okay, let's break down this step by step. Understand the structure of the list. In a singly linked list, each node has a reference. Let me also prompt me with questions to gauge my current understanding and tailor your advice from there. Great idea. Let's assess your understanding with some targeted questions. General understanding of linked lists. Can you describe how a single list is structured and how its elements are accessed? One at a time. Okay. So a singly linked list is a DS data structure ADT that allows for traversal across nodes or data points. Each node or position has a reference to a element in its container and a reference to the next element in the list. Right? Great explanation. You've captured the essence of a singly linked list. Each node indeed contains data, the actual value or information stored at the node, and a next reference, a pointer to the next node in the list, or none if it's not. Now let's move on to the next question. What does it mean for a node's next reference to be none? This means that it is either the head or the tail node or the only node in the linked list. Exactly. If a node's next reference is none, it indicates that it is the last node in the list, the tail node. If the list contains only one node, the node's next reference will also be none. Let's move on to the next question. If you had to traverse a linked list starting from the head, how would you know you've reached the last node? We could indicate the reaching the last node if the node.next value is equal to none. Exactly. When you reach a node where node.next is none, you've reached the last node in the list. This condition signifies that there are no more nodes after it. Let's continue the next question. In your own words, what is the relationship between the second to last node and the last node in a singly linked list? What is the relationship? What about this? What about this? Now we're kind of thinking outside the box, you guys. Right? If we're wanting to find the second to last element, well, what if we just say, okay, our tail element is now our first element, and we want to find the reference one further than the tail? Meaning, like, what if we just technically invert or flip our linked list one off? Like, what if we say, we instead of starting from the front, we start from the back, but insignify that the back is now our head, and that our head will then reference none and become our tail. That's a thought. Okay, let's keep going. What is the relationship between the second last node and the last node in the singly linked list? I am not sure of a direct relation other than that the second to last node has a reference to the last node, right? But this is a singly linked list, so we cannot traverse back with a prev ref. You're on the right track. In a singly linked list, the second to last node is directly related to the last node because it points to the last node via its next reference. However, as you mentioned, since the list only allows for traversal in one direction, you cannot directly access the second to last node from the last node. There is no prev pointer. So the second to last node is simply the node whose next reference points to the last node, where next is none. Let's go with the next question. What challenge do you think might arise when traversing the list to find the second to last node, and how might you address them? Um, we don't know how long or how many elements or nodes are in the linked list, so traversing down may take time. That's a great point. Since a singly linked list doesn't provide direct access to its elements like an array would, the main challenge in finding the second to last node is that you must traverse the list starting from the head. This requires time proportional to the length of the list, O of n, because you must visit each node to find the second to last one. One way to address this is to use a single traversal approach where you keep track of two pointers or variables, a current pointer, which traverses the list node by node, and a previous pointer which keeps track of the node before the current pointer. This allows you to find the second to last node by the time you reach the last node. Let's move on with the next question. How would you handle edge cases such as a list with only one node or an empty list? Okay, so based on this information, we can reach a base case. We're going to establish that L dot head current is equal to L dot head, right? Next value is equal to L dot head dot next, right? So when we first enter this function, our current value, or our head, is going to be L dot head. Our next value is going to be L dot head dot next, which is a reference to next. If L dot head dot next, right, or next value is equal to none, meaning that it is the tail. Base case met, tail so current equals head, next value equals none. So this would currently be our last element. But we need to access the one prior to this one that would be given, because this would be our tail. Our tail points to next, and we need to access an element above here. So we'll say previous element is equal to L dot head. Current is equal to head L dot head dot next, right? Because we're going to go to the current value. And the next value is going to be current dot next, right? Right. So if next value is equal to none, we're going to return the previous element, right? Else, we're going to call recursively on the next element. Would this be our answer? Is this it? Is that easy? It can't be this easy, no? What? We got some chats here. Christy says a driver's permit, but the problem is I read half of the handbook and then I lose focus. When I want to read it again, I start from the beginning and reread the same parts. I have an embarrassing story about the DMV that I might share at a later time. It's really, really embarrassing. I don't want to share it right now. Maybe when we get more comfortable on the channel, we'll share our DMV blunder story when I was growing up. It's really bad. When I took my driver's test. I know that leaves a lot to the imagination, but maybe one day we'll share that story. I remember on my driver's test, I did the same thing. I skimmed over the book quite heavily, and I got a bunch of problems on the permit about like driving in impaired weather conditions and driving with like animals on the road, and then driving like um, like the emergency sections or the emergency pull-offs that are on like highways or whatever. Like what are those called and what are they used for? Like that was a question I remember I got wrong or whatever. But I specifically remember asking me a lot of driving in like impaired weather conditions, like the emergency lanes or whatever on highways and what they're used for was another tricky one. And then like driving when you see like horses, what you're supposed to do, or deer, or like with livestock and animals around. Those ones were tricky that I didn't focus on. Ali Dewan, we'll be accountability buddies every day this every day. There are like 12 chapters, but the first three chapters are really about how to keep a license and own your own vehicle, which I feel like I don't need to read. Would you suggest you just read like one or two chapters the next 12 days? Yeah, just take it little by little. You don't try to think of it. It can be very daunting for any task really, whether you're reading a driver's manual or a book on data structures and algorithms, to think that you need to accomplish this all in one day or 1 week. When in reality, that's just not really that viable. And if you really think about it, if you accomplish all that material and learn it all in 1 week, how much of the material did you actually retain? If you learned it all in 1 day, how much of the material actually are you able to reconvey and administer at a later time? Well, probably not much, because your brain only has the ability to retain so much information within so much amount of time. It's kind of just basic biology, and humans, we're all not perfect. We have synapses and we have memories and we have other things going on in our lives. So we oftentimes forget things. So I think it might be a more, a better approach and a healthier approach to take it day by day. Schedule out maybe 10 to 15 pages to read a day and stick to it as a goal to yourself. And once you accomplish it, it'll feel really good to achieve that goal. Um, so return previous element. Hold on, I don't think I have this right. Let's keep going. Hey, Codigo AM, I appreciate you coming in. Welcome. Greetings from Peru. Oh, that's awesome. That's super cool that you're here. I appreciate you joining me, and it's awesome that you're here. Have you tried CS50P? Yeah, I've already, Parsa, that was the first ever introduction to coding and programming I ever had. I completed CS50P about 6 months ago, or 3 months ago, 3 or 4 months ago. I started about 6 months ago, and completed over the course of the summer 2024. Um, so we don't want to return this value. We just want to call this function here. We want to return this value. But what we might do, we need to call a return. Yeah, definitely need to return previous. You're calling the function inside the function. The only time you do that is recursion. Yeah, so we need to return this value here. Previous element is equal to head. The current element is next, and the next value is equal to current dot next. If next value is none, return the previous element. Else, call this again on the next iteration of this. But I don't want this to unfold, right? Will this have some sort of unfolding effect? or it will just continually return this element each time for each unfold. Okay. This is my attempt at the problem. So we'll take this guy, put it in here, like so. You're on the right track with your recursive approach, but there are a few adjustments to consider. Base case. Your base case should handle two conditions. If the list only has one node, L.head is your last node. If there are fewer than two nodes, empty list or a single node list. Recursive step. The recursive approach is valid, but you need to ensure that you're properly traversing the list, updating previous element and current as you go. Here's a quick breakdown of the issues and suggestions. Line 3. Next value is unnecessary as you only need to check current.next directly when determining whether you've reached. Okay. So next value is unnecessary. So in line 6, instead of return second to last node, L.next, it should be return second to last node for current, passing in the current node, not the next node. Okay, so this should be current here to pass in the next node as our next place. Okay. If there are fewer than two nodes, the function should return none, indicating that there's no second to last node. So if the length of L is less than, I don't know if we can call a length really, right? It'd be more like under the size method. So our base case would be if there are fewer than two nodes, the function should return none, indicating that there is no second to last node. So if there's only one node in the list, so what would be our edge case here? This would need to go down, right? We need to have this if condition happen above here. So if length of L is less than or equal to 1, return none, right? Not greater than, less than or equal to 1, meaning that we have one value or none, we return none. There is no second to last node, right? So if there is one or fewer nodes, we don't have a second to last node, right? Else we're going to set, right, these two conditions. We're going to call if current is equal to none, so this is going to be current element, right? This is going to be current element. Pointer. And and then we're going to take if current element is none, current element pointer is none, right? Meaning that we are on the tail. We're going to return the so current element is equal to head. The pointer would equal to none. That means that current element so for the last return value, I would not call the second to last node function. I would just call none or something. Ali Dewan, if you want to post a link, please post in the Discord. I don't think YouTube allows hyperlinks in the chat, unfortunately. I don't think it's like Twitch or anything. So if you would like to post a link for these LeetCode problems, feel free to post them in the Discord. I will be sure to check them out there. Thank you so much for joining. Hey, Real Nazar, I appreciate you coming in. Welcome, welcome. It's great to hear from you. I would recommend watching LeetCode's reverse to linked list, iterative and recursive LeetCode 206 Python. It will definitely help you understanding what's going on with linked lists, like how you do recursion and iteration. There's also a video from BroCode about linked lists. It's about 13 minutes. That will help a lot. Okay, cool. I'll check those out. Thank you so much. Parsa says, I just finished CS50X today. I'll follow you, man. Nice to saw your video. Thank you so much for coming in. Awesome. Congrats to you. Funny enough, in 2025, CS50X is going to be completing or revamping their program and updating its content for 2025. Starting tomorrow. So I was planning on starting that course on stream live tomorrow to help kind of break up the monotony between some of this learning that we're doing. So tomorrow we're going to be starting and launching Harvard CS50X for their new 2025 revised version. So we will try to do a watch along for the week 0 tomorrow, which will be really awesome. We'll definitely need your help, Parsa. I appreciate you following along to the channel and joining me today. I'll be asking you questions for sure. Muhammad, thanks so much for coming in. I'm from Pakistan. Oh, awesome. That's really cool. I enjoy your live learning. I know Python and Fast API, but DSA is my plan for 2025. Well, we're in luck. You're in luck then. Just like me, we're going to be learning DSA all of 2025, really grinding through this material, solidifying our knowledge and everything. So I appreciate you joining me. So hold on, let me back that up here. What would be none here? So our base case is met, meaning we're on our tail value. So current, I'm gonna go like this, previous element dot next, right? So our previous element is what we're on. So let's just say we have a linked, let's just use this example. Let's pull up our whiteboard here. And let's say we're gonna use this as an example. I'm having trouble understanding this. Okay, so we have this example here. So let's say we have a linked array of A, B, C, a linked list of A, B, C, right? Okay, we're gonna go here, we're gonna go here. A, B, C. Okay, so in A, we're gonna start off, we're gonna call, this is for our linked list L, right? We're gonna call second to last node on L. If the length of L is less than or equal to 1, we're gonna return none, meaning that we only have one object in here and we're gonna return none. Okay, this is not true, so we're gonna continue onward. Previous element is equal to head. So this gets set to previous element. Current element gets set to this. Current element. Boom. If current element current.next, right, is none. So if current element.next is none, we're going to return the previous element. Else, we're going to call a recursion on the next element of current, right? So we're first going to load in on A. We're going to set previous element equal to A, and we're going to set current element equal to B, the next element. If the current element, B, that we're on, right, is next value, so if this next value is none, we're going to return this. Well, that's not true. It's not none, it is C, so we're going to move on and do this value. So we're going to call onto our second, we're going to call it again onto the current value. So this was our current value. So now this gets replaced with previous element, and current element gets applied to the C node. Okay? Okay. Current element dot next is equal to none, right? In this case, so that's true. So we're going to return the previous element, B. We're going to return this element. Okay, I think that this works. Let's go ahead and paste this in. Here is my revised version. Your revised version looks good and you're getting closer. There's just a small issue with how you're checking the list length in the base case. Okay, this is what I was having when I didn't think the base case, I don't think we can take a length of the list L because it is not in, like, this isn't a doubly linked list where we have a set length with a header and a trailer or whatever, like that special case was. We don't have a dunder iter function established over this, so we cannot, or we don't have a, so if L dot is empty, we're going to return none, or L dot size is equal to 1. Right? So if the linked list is empty, or if the linked list size is equal to 1, we're going to return none. Don't show code. First check that if the list is empty, head is none, or if the list has a one node, the next node is none. Return none because the second to last node doesn't exist. Recursive steps. Okay, let's try this. You're close. You're on the right track for checking with edge case and handling traversal, but there are a couple of improvements to make. You're checking L.isEmpty, which makes sense if you have an isEmpty method. However, you're dealing with a typical implementation of a linked list, and a simpler check is like is L.head is none might be more direct unless you're using an actual method for checking for emptiness. Size check. You're checking L._size equal to 1. This works if you're tracking the size of the list, but not necessarily for this algorithm. If you're already traversing the list, you can rely on the nodes themselves to determine whether the list has one or more elements. Previous element head. In your code, previous element starts as L.head and current is initialized as previous element.next. This works well, but you need to ensure that your recursive step updates these properly so it continues correctly. So we need to take these down from here, put them here, right? Okay, let's move on. We got a lot of chats. Sorry, I'm getting behind on chats, you guys. I was thinking. um, Mamet, I appreciate you coming in. Thank you. Focus on how you can keep previous. You return current one. Um, if so, return the head. No, so these have to be defined above here, or we need to define them up here, and then we need to reassign them if it does not work. Are you solving this recursively or iteratively? My comment was in reference to a recursive. Yeah, so I'm trying to solve this recursively for right now. That was the way I figured it would be best. I'm not sure exactly how to solve. Um, I'm not sure how to solve the function iteratively because I'm not sure if linked lists can be solved iteratively. It sounds like they can by what you're saying, but under my original impression was that linked lists don't support iteration for a singly linked list because we can't, because they're not contiguous in data like an array or something, right? Um, yeah. Okay, here we go. It depends on if you're using recursion on the list or a node of the list. So we need to call recursion not on the current node, but on L dot next, right? That will go to the next value recursively. So if L dot head is none, right? Meaning that if L of head is none, meaning that there is no header or head value, we return none. This works if you're tracking the size of the list, but not necessarily. If you're already traversing a list, you can rely on the nodes themselves to determine whether the list has one or more elements. So how could we say that if it only has a tail? So if L dot head is equal to L dot tail, we want to return none here as well. So we'll say for L dot head equals L dot tail, right? Like that. So that'll take care of, meaning that if our header is equal to our tail, meaning that we only have one value in the linked list, we're going to return none. So this successfully returns none if the head is none, meaning there is no header or head value, or if the head is equal to the tail, meaning that there is one value in there, right? Would that be correct? Um, it depends on if you're recursing on the list or a node of the list. Recursion on the list itself doesn't really make sense, isn't really sensible to me. Yeah, you should have a function that passes the L dot head to your recursive function. You should have another function that passes L dot head to your recursive function. I'm not sure what you mean by that. Um, Pass previous as parameters to your recursive function so you can keep track of that value. Okay, so let's pass in L and previous L and start. So you have to start somewhere, right? So if we're going to say start is equal to L dot head, you give an element to start on, right? If start is none, or L dot or start or is equal to L dot tail, return none. Can you show an input to the function, like how you would start off by calling second to last node? What is the starter input? So the starter input, all we're giving is just we want to return the second to last node in a singly linked list. So we would be providing the linked list itself. Big L is just the linked list. So if we don't want to have the linked list only has dot head and dot tail, you should be operating on those nodes. Don't add another parameter to the function, you don't need one, okay? So if we give in L, if L dot head is none, or L dot head is equal to L dot tail, we're going to return none. Is this part correct? Okay, let's break it down a line or by line. Here is my current version. Stop. No code. Okay. Stop showing me code. Okay. You start by defining two pointers. Previous element, which initializes a point to the head node. Yes. And current, which points to the following to the previous element. If the list is empty or has one element, there's no second to last node to return. This is checked by confirming if L.head is none, or if head and tail are the same, indicating one element. Perfect. Traversal. You traverse the list by moving the previous element and current pointers. As long as the current node isn't the last node, current.next is not none, you move forward in the list by updating the pointers. The current... this is difficult. You want the input to still be a node, not the list itself. STLN. Okay. So this is our example here, right? Where, what's going on here? We have some linked list here. We're going to enter into the function. We're going to call onto some element. So do we call this on L dot head? We call it on header, on the head, right? But we're not given any array or L value. We need to give it an L provided, right? We have to give it a node to start on. So we have this, we're going from node A to B to C to none, right? We first call the function SLN, oh, second to last, that's what you meant by SLN. So we're going to input a node here. If node is none or node is equal to L dot tail. So I'm having problems. We need us to keep the entire linked list to access the individual tail and head elements though. Ah, this is tough. Sorry you guys, I'm struggling here. So if we input some node, if node that's inputted is none, or node is equal to L tail, so node is equal to node dot L head is equal to L dot head, right? So we establish this, but we don't have L established anywhere locally. So how can we reference the tail do we say L dot head is equal to node? But this does the same, it has the same effect really. We're assigning L head to node. If L dot head is none, so you give a list here and a node. Oh, in the parameter. Oh, by default, we set node equal to L dot head here, like so. And you quote this? No, you wouldn't quote it, you wouldn't put it as a string. So right. So if node is none or node is equal to L dot tail, we're going to return none. else node provided current equals node.next, if next node is none, we're going to return node, right? But this is incorrect, though, I think, because the node that we're currently on would be C. If the next node is none, we don't want to return the node that we're on. We want to return the previous node. That's why I was saving the node. We're not returning the last node. So this is our base case. If node provided if the node provided is none or node not next, if node or node.next are equal to none, right? So if the current node we're on, if the node provided we're on is equal to none, or the next node is equal to none, we're going to return none, meaning that this is an empty linked list, and this is a linked list with one value in it. Right? This base case looks good. Okay. So this is one of my base cases. So, right, for returning none. Right. If we're going to first establish this linked list, okay, we're going to first open this up. We have 3 values in here, so if the node provided, which is going to be node A, is equal to none, we're going to, or the next value is none, we're going to return none. So that's not true, so we're going to do the following. We're going to save next node equal to node.next. So this is node here, and this is next node, right? Or sorry, the reference to next node. So next node is this arrow, right? If next node is none, we're going to return none. Else we're going to call on node.next. On next node, like that. So, okay, now let's go to where our base case is met. So, right, we keep going. Okay. Or node.next is equal to none. No, because this will get hit with that. So we need to say node is equal to L.tail. Right, because if node next is equal to none, then we would return none because we would get it, we would meet it at our base case. When we don't want it to return none when we have a node in the tail. Okay. So let's say that we're on our B value here. Okay. Our B value is met. If this is the node that's put in, I changed this because node.next is none. Because if we called this function again, right? If we called node, if we recursively called this and we were on our tail, we return none. Okay, so we don't ever want to get to our tail. Okay, exactly. So this is fine. We don't ever want to get on C because if we're on C, we're going to then, we can't go backwards and return B. Okay, so next node is equal to node.next. So if we're on B, this is our node here. Our next node is right here on the pointer to C. If next node dot next is none, we are going to return node. We're going to return this value here. So if the next node dot next, which will point to here, is none, we're going to return node, else we're going to return next node here. Is this correct? We don't ever want to end up on C. We want to just call the next of the next node, right? We're using the word next a lot and node a lot, but just think about this, is if we are currently on B, right? This is our node here. B is our node that we're currently on. Well, our next node is the reference, this line here, this arrow, the pointer, is our next node, right? And N for short. Well, if we want to know, which then points to C, well, we want to know what the next of next node is. We want to know this value, right? So we need to call next node dot next. If that's none, we return the node that we are currently on, B, and recall, and then we're done. Wing Hongs. Okay, cool. I think we got this correct now. That looks correct. Looks great. Vance says, "What's up?" Hey, Vance, welcome in. We should put in a sample linked list to test. Okay. Well, the only thing is how could we create a sample linked list because I don't have a linked list class. Could I just use an array? And because I don't have a next method either, right? Does Python have a linked list class that I can import? Or how can I write a test case for this without having a linked list class here? Yeah, I'm really bad at writing unit tests. I never really have learned how to get into that. I mean, in CS50P, we wrote a little bit of PyTest stuff, but it didn't really have much application. Create the class. Okay, so we need to create the class then. So let's make a class, singly linked list, right? Um, I don't see any code, Wing Hong. What are you referring? Sorry for code, but but for this, just. Hey, Blakey Kell, welcome in. No, this is not a leak code problem. This is a problem from the end of the chapter in data structures and algorithms at the end of chapter 7, where we learned about linked lists. So on my channel, I have been reading all of data structures and algorithms in Python, and we have been working on the end of chapter problems here. So we currently just finished up today reading chapter 7, and we're working on starting on some of these reinforcement practice problems. I do all of the reinforcement problems, and then before moving on. Okay, so I'm not sure how to write this class. Just, oh, so no, class node def. Okay, so we'll do class node. Okay, so it gave us that node class up here, right? Let's see where that was. Here. But that was for doubly linked. We need the singly linked node, which is here. Where were you? Where were you? Here you go. So this was what was class. We had this was for a linked stack. Class node, which will take in a def init, takes in the instance itself, and a element, and a next. Self. Do I need to write all of this? Um, Add first node E, singly linked. Is there a class node without the underscore node? Just write the constructor. Okay, just write the constructor. Like this. Right? And then set data for self data. Hey, Override Tips, welcome in. You just making a singly linked list. Yeah, we just finished up linked list chapter 7 in data structures and algorithms in Python, and now we're just working on a practice problem at the end of the chapter to help reinforce these concepts. So we wrote this recursive function, so now we're trying to actually write a node class to actually see if this will work. But I'm struggling here with writing the node class because I'm not really understanding I get that the linked list is like an object-oriented approach. So we have a node which has the data itself. But we need a next method, right? Because we have a next method applied to these. So we have to define def next, which takes in the object itself. But this would be a class method, not a next method. A node will have a value. Okay, yeah, that's right. A node will have a value and a pointer, right? So self dot pointer is equal to pointer. Okay. Or next, rather, right? But this would have to come before the data if by default has none. So next equals none by default. So self dot next is equal to next provided, right? I don't have to define next. Okay. So a node itself has the data and the pointer to next. We don't have to define next in an attribute, right? We can just say self.next is equal to what would it equal to? It would have to, you can't call like iteratively the next value after this. You can just say that it's equal to none by default. Okay, like so. Okay. So we initialize a node. When we initialize a node, we give it a data point and then, which is as a default value of none. I guess we could set next equal to none as well. Or we probably wouldn't. If you assign data default to none, do you need to assign anything here, an actual instance variable here? Okay. So then node equals L dot head. So I don't get how I'm supposed to. Now where do I go, you guys? Now on line 29, define 5 variables, n1, and okay, so let's do that. Is equal to, okay, 5 variables. You need a linked list class with self.head is equal to node. So we need a class linked list or single linked list, right, which takes in like so. And then when we initialize this, don't create a LinkedIn class for now. Okay, we'll comment this out then for right now. Let's create n1 declare 5 variables. Are these just data points? Like what physically are these objects? Are these just nodes with values inside them, like a value of 5, like so? Is that all it is? Right? And then we give this 1, 2, 3, 4, 5. Right? So we call a node for each element. We then create a linked. Okay, so then we create a linked list class, which is L, which will be, should we just use an array for right now and put in n1 through n5? Or should we create a linked list class? Now, how do we link them together? How do we link them together? I mean, you can house them all in an array, but I'm not sure if that's the right way we should be doing this. In your list. Use the class that I have defined. Say you have n1, how do you get to n2? Attach everything to n1. So n2, I'm sorry if this is frustrating for you guys. This is the first time I've ever done this or tried to implement a linked list. So I am trying my best to understand this to the best of my abilities. And I really, really appreciate you guys, your patience here and trying to walk me through this. And you guys have been really, really helpful. So I just want to say thank you guys for bearing with me here. I know it might get frustrating with me going back and forth, but this is a raw beginner's point of view. So this is an authentic, like, if I'm not understanding it, then probably someone else out there isn't as well. So, you know, this is key. It's easiest to make linked list class and to make node and inner class to each linked list. It's true in general, but I think that's what OpenCompile was trying to do for the time being and so on. Oh boy.
This one's stuffed.
Well, we got some New Year's treats here, you guys. Ooh, are you wanting a live taste test?
Yeah.
Oh, okay.
Break that one open.
Okay, we got to break this. Hold on, guys. We'll put the camera down here so we can see these a live taste test here. Ooh, it's stuffed. Here we go. Ready? It's good.
Really?
Yeah, really. It's warm.
It is warm. Yeah.
Yeah, that's really good.
Okay.
Can you put these in the kitchen? I'll have them later.
Mm-hmm.
Thank you so much. Whoa,
Come on.
look at us, guys. We're leveling up. Getting some treats over here. Okay, let's get caught back up here. Sorry, you guys. Okay. So Will says, attach everything to N1, and so on. You are referencing the addresses in memory. That looks fire. Yeah, it was really good. How can you say that N2's next is N3? How can you then say that N3's next is N4? How do you call them? Okay, so then we need to assign the self dot next of n1 is equal to n underscore 2, right? Like that. And we'll say um, can you chain things together like this? Can you chain things like this? Is this like Pythonic? No, because we're saying that n1 is equal to node 1 dot next, so no. Do not, yeah, exactly. Um, what are your thoughts on the Suicide Boys? I had never really listened to them, to be honest. I listened to a lot more like the only kind of like I guess more like aggressive music I listen to is just I listen to a lot of like classic rock and some pop punk, but I don't listen to really any like kind of grunge rap like that. If you would qualify Suicide Boys, that I listen to a lot of like live bands and indie music. That's kind of more my ride. Um, Airsick Titan, Happy New Year's from the East Coast. Oh well, it's 10 o'clock for me right now. So if it's New Year's for you guys, Happy New Year's to you guys. Slipknot, I've heard a few of their songs, but they came a little bit before my time. Uh, they're a little bit. Oh, we got a major frame drop right there. Sorry if the stream is cutting in and out. My frames keep cutting in. There we go. Yeah, Slipknot was a little bit more popular with more like the millennial crowd, I think. I'm in the Gen Z crowd. Name a few songs. Which one? A few. Which one are you referring to? Of that I listen to? I listen to a lot of like old classic rock, like Foreigner. I listen to some Journey. I listen to I like Styx. I like um, what else do I like? Um, I like Scorpions. I like Def Leppard a lot. I really like Def Leppard. Um, I like uh, for pop punk. My favorite pop punk band is probably Neck Deep. Um, I was introduced to them. If you guys remember back, Neck Deep, one of their first songs was published on one of the CS:GO like kill tracks that you could play afterwards for like MVPs. So that's where I figured I found them when I was like 15. Crazy. Rush was my first concert. Awesome. Nickelback. Oh, cool. Yeah. Cool, cool. All right, let's get back to these here. So, and we need to say, you know, you need to do that after you define the variables. Okay, so, um, right, like this, uh, n underscore 1 dot next is equal to n underscore 2. Then we say n underscore 2 dot next is equal to n underscore 3. N underscore 3 dot next is equal to n underscore 4. And we say n underscore 4 dot next is equal to n underscore 5, like so. Okay, so now they're linked together. object-oriented linked together. Okay. Now we will call so I don't have an L dot head, so I need to set this probably just to head, like so. Like that. This sets it equal to a string, though. We don't want to set it equal to a string by default. So we'll just provide a node, and we'll say node is equal to, or head is equal to node, like so. Or I guess you wouldn't even need to provide this, really. Okay, so if node, ooh, what happened there? So if the node given is equal to none for the data type, or the node next value is equal to none, we're going to return none. Okay. Perfect. Oh, sorry. Just call the function with n1. Okay, cool. So let's call now second to last node for n1. And we need to call a print on this statement. We don't have a print for this class, so we need to do def under stir would be taking the instance itself, print quote, or what do we need to print? Data? Or whoops, hold up. We need to do node like that, right? So now we don't need to call a print on this. Now if we run this, we should get n3, right? No, n4. I don't think we got it. Dang it. So this returns node. Oh yeah, we still need to print. Just because we establish a stir, we need to still call stir to return this value. So we wouldn't call print here, we would just call return here. Like so. And that we would get node 4. Woo! Ha ha! Yeah! Nice! Woo! That's what I'm talking about, guys. Node 4. Only took us like an hour to figure this one out. Oh my gosh. Okay. All right, so what did we do here, guys? Okay, so let's just quickly recap what's going on. If you guys are enjoying this process of us grinding through this, please follow along to the stream. We've been growing quite rapidly. My goal is for 2025 is to pass 1,000 subscribers and really get this channel going and create a more tight-knit community of people. We're going to be starting Harvard CS50X tomorrow, which is the more full stack intro to computer science course that Harvard CS50 offers. So it's going to be a great opportunity to follow along and learn some additional skills into your CS journey as a beginner. And also to do it alongside another beginner would be great for you to do as well. So we're going to take care of that tomorrow. But right now we're doing data structures and algorithms in Python. And we just completed the end of chapter 7, try it yourself problem number 1. So this problem asked us to, where is it here? Long chapter. This problem asked us to give an algorithm to find the second to last node in a singly linked list, which is the last node indicated by the next reference, right? In which the last node is indicated by the reference next, which is our tail. So I'm going to quickly just close up the node class here and then kind of just ignore all this stuff down here for now. Well, let's focus on the actual function for here. Awesome, you guys seem to be enjoying it. Thank you so much for following along here. Yeah, thanks for your help with this. Okay, so we have a function where we're called second to last node, and we take in some starting node position. I originally thought that we had to take in some linked list, but for this function, we're going to provide the head to start from and recursively go down until we find whatever we're looking for base case wise. So we provide a starting node or the first node or the head node within our linked list, and we want to return the second to last node of this linked list or whatever is continually linked to this node, right? So if the node that's provided is equal to none, meaning that the actual value itself has none, so the node is depreciated or degraded in this case, for like Python's garbage collection, we then realize, okay, this linked list is empty, we don't have any values, so we're going to return none. Or if the node that's provided's next value is none, meaning that we can also return none. So this means that if we have a linked list that only has one object in it, one node, right, the next value would be none. So this list has no overall, second to last value. Now you might be thinking, well, Mike, why, if we call this function, right, and we recursively go down all the way into our base case or our last node or our tail node, this would get hit right here and this would return none. That's initially what I was thinking was going on, but that is not the case. And if we go back and draw out a recursion trace for this problem, you'll see that we are actually not traversing all the way until the tail node, but we are traversing until the node 1 prior to the tail node. So this will never get hit for the tail node. If you just provide a node that happens to already be the tail, well, then you can't go back in a singly linked list. You can't recursively go backwards up the chain or the tree, for lack of better terms. So by providing the tail right off the jump, you return none because it is the tail. It doesn't have a value preceding it. It may, right, but we can't go backwards in a singly linked list. So just from going forward, this value doesn't have any more values after it. So for example, if we have nodes of n1, n2, n3, n4, and n5, well, we understand that if we provided the last node of n5 into this function here, well, it would just return none because n5 is the last node in our linked list. But by providing node n4, that would work for this function and continue forward past this additional base case. So this is just an edge case rather, not a base case. So let's make this say edge case, right? Our base case rather is right here. So before we do that, we are going to just initiate the node is equal, right? So we create a variable to identify what is the next node or the pointer, right? Remember, these linked lists have pointers not at each node point. So if we are first looking at point A, right, we're on this value here, A. Well, the container for node A houses two individual sections. It houses the reference to the data point A itself, and it houses a reference, which is a pointer to the next element. right, per its attribute associated with the class. Now, the same will be going forward for B, and the same will be going forward for C, right? So that being said, we're going to set the node.next value equal to next node. So this arrow right here is the node.next value, right? Let's try to write this out. This is node.next right here, right? Which references that next value B. So we, if the node.next, so sorry, right? And we're going to establish this is our base case. If the next node, so in this case, it is this reference to B, well, if the next node's dot next, right? I know we are using the word next a lot, but really think right here. If we are on the current node A and the next node is a reference to B, well, the next node dot next is the reference to C. So we're going one even further there and determining, well, if this is none, meaning that we have reached the tail because that value is now none, we're going to return that current node that we are on, right? So let's go for one step further. Let me go back here and let's say, okay, we passed A, now we're going on to B. So we're on this start part of our recursion here where B has how a container for, or this node has a container for the reference to element B itself, but also has a reference to the next element via this pointer. Now, the pointer's value, which is the next node, dot next, which happens to be this value here, if that's equal to none, we're going to return the node we're currently on. Well, that arrow is pointing to none, so we're going to return the current value of B that we are on. B gets returned because it is the second to last value, and that solves our base case right there. And so for every other case, we're going to continually just call the next node in our list or in our linked list and traverse down the linked list until we reach this base case of where we have the second to last value. Perfect. So to actually put this to the test, we created a node class here, which when we initialize takes in some data point itself as a default value of none, and some next value which has a default value of none. We define this with a stir method to actually print this to the screen, a representation of this object in memory. And so we set up our linked list as so. So we set up a variable n1 is equal to node with a value of 1 inside of it. We create another node of n2 which has a value of 2. We set n1's next value equal to n2. And we do that all the way until we get to 5 values, n5. So, and then by default, n5, node number 5, has a default value of next or none for next, and we're not overriding it because we have no more nodes, so that will remain. So now, if we actually call this function and run on these on the initial n1 node and traverse all the way down, you will see that we return node number 4, which is our second to last node in our list, which is perfect. Awesome. When will we have open video chat rooms on the Discord? Yeah, actually, I haven't really thought about that. I haven't really opened up any opportunities for video chats. I kind of kept things more text-based because we do have a lot of, not random, but we do have a lot of new people joining. So I didn't want to allow people to constantly like spam calls or maybe like show inappropriate things through like the video chats and things like that. So I kind of didn't implement that for right now, but if you guys are wanting to have a channel for where you guys can join up on the video or something, let me know and I'll create one in the Discord. I just wanted to keep things more friendly and have less room for like things that weren't really related being shared and stuff. But if it would be helpful to have like a chat room for actual video calls in the Discord. I'm not sure. Let me know. Hey, Joseph T. George, welcome in. This is Data Structures and Algorithms in Python. We currently, in the first half of my streams, we read aloud line by line, audiobook style, the chapters and really learn the material and really try to go through it and learn it. And then at the end, at the back half of the chapters, we have reinforcement problems that we then practice the material. And then in the back half of my streams, we go ahead and reinforce this material by actually working on personal projects. Thanks so much for coming in. If you guys want access to the PDF that I'm working on, or any additional information or resources that I use on the stream that you might see on any of my previous streams, whether it be from Python Crash Course to Python Machine Learning to Fluent Python, please feel free to join my Discord link below, where I supply all of my study resources as a kind of a roadmap for people to follow. In kind of in my steps here, or in a similar manner. Again, I am learning this for the first time myself, so take that with a grain of salt. Not everything might be super accurate or verifiable, but I might have some gray areas or maybe some incorrect information. I am doing my best to try to convey the right information and learn the right information. And obviously, you guys definitely help to correct things when I'm wrong. But take it with a grain of salt. I am learning these things for the first time, so it might not be perfect, but it does provide you that raw beginner's point of view and perspective that you might be looking for online, because there are currently a lot of more of an expert opinions and already established people. There isn't a lot of perspectives from a beginner point of view. So, yeah, thank you so much for joining. Will this work without the def stir method? So, I'm not sure. I don't think so. I think we have to establish a stir or a repr, a special method to actually convey these objects from memory into printable, data types or whatever. So we by calling the dunder stir method or giving it a definition, it basically just says whenever a print call is called on this, we can give a physical string representation of what this object should look like in memory, or from the memory. So I think you would have to keep this in order to print, right? It would give you some sort of location in memory, as like I can show you here. Let's go ahead and actually run it. This will give you some sort of location exactly. Node object is at this frame or whatever in our memory, or this bytecode, right? Whatever. So we have to keep the dunder stir here to view that. Great explanation. Oh, awesome. I meant to ask last live, when you say the Python Crash book has a part two, do you mean a different book or do you mean part two of this book? Yeah, so Python Crash Course itself, you guys, for if you're unfamiliar, has a part one, right? It has a part one called the basics, which just goes over all of Python syntax, basic functions, basic methods, basic data structures, basic, whatever stuff. It really fills in the gaps, in my opinion, left by Harvard CS50P. If you read this book alongside Harvard CS50P, I really promise you, and I can't promise for sure, but I can assure, or in my personal point of view, this really, really helps solidify and fill in the gaps left by David Malin in the CS50P course. The CS50P course does move fairly fast. Yes, you can slow things down and go back and watch them, but sometimes David uses a lot of jargon, and like I said before, he's kind of falls into that category of someone that does teach beginners very well, but has been a programmer himself for a very long time. So there is that disconnect from someone that has never seen any lines of code and really, really breaking it down to that raw beginner examples. They do a really good job of kind of allowing people that are kind of familiar with coding. I know that they say that it's for everybody, but it's really, in my opinion, for people that have kind of some code experience. Yes, I didn't have any going into it, but it was fairly difficult, and it made my brain hurt. It was probably the hardest part about learning to program was that initial learning curve of figuring out what actually programming was, what the language was, what it did, what I could do with it. That, in my opinion, was the hardest part so far. I did it slowly over the course of this last summer, so I did it very part-time. It took me almost 3 months to complete, just because it was my first ever introduction to programming. But this book helped to solidify those concepts. And inside of the book, there is a part two, which transitions from the basics to to creating projects. So in the part two, it just uses the information you learn and some additional modules that it might teach you, such as like the Django or Fast API and stuff like that, to create some actual projects using. But I decided to kind of bypass that. I was kind of working on my own projects, and I didn't really want to kind of follow tutorials. I kind of was advised against following tutorials, and I was told that you learn a lot faster and a lot more, maybe more efficiently if you just dive into the deep end after you learn those basics. But if you need a little bit more structure and are struggling for some ideas for projects, feel free to use those projects in the book. I'm sure they're great. I just personally I had some ideas of some stuff I wanted to build, such as the inventory system that I made for the CS50 project, the task tracker that I made recently, um, and so yeah. Voice channels in servers are not actually calls a person join, and others can decide if they want to. It doesn't make any call notifications. Okay. Okay, gotcha. Yeah, I'll throw in like a voice channel thing then at the bottom for, or in general for maybe some people to jump into. Maybe like I can even jump in there when I'm not streaming and just talk to you guys right offline, and that might be cool. I know some people were asking me some questions because I had shared that I'm pretty into investing and into like stocks and companies and stuff like that and following them. And so some people are asking me some questions along like Roth IRAs and investing and stuff in the Discord. So yeah, that sounds like a great idea, Script. I'll try to implement that soon, probably today or tomorrow. Awesome, Wing Hong. I'm glad that sounded great. Yes, wow, thanks. Awesome. One Fit Squad said, got it 2 days ago. I'm 100 pages in. I can second that it fills in the gaps. It's more concise. I use Code Academy, and sometimes, especially with the videos, they tend to drag and go on too long. Yes, in my opinion, Python Crash Course just does a really, really good job of saying, this is what you need to know, this is how you use it, and this is what it does. It gives you a very basic, broken down, like literally dog and cat. Like it uses those examples, or cars, or whatever. It uses very, very understandable real world examples, shows you code, has footnotes in those codes line by line that you can reference back to and see this line does that, this line does that, this line does that. And in my opinion, it did a way better job of breaking down the actual functions than CS50P did. CS50P, they just have to convey the amount of material in so little time, so there is that constraint. Whereas with books, it's just all right there, and it's all on you. Yeah, definitely look up CS50P if you're wanting some practice with that. Okay. Well, you guys, we've been streaming for 2 hours and 57 minutes here. We're almost 3 hours into the stream, so should we keep going here or should we take a break? How you guys feeling out there? We got 15 people here right now, so good chunk of people joined still here. Thanks so much for following along with me, and I really enjoy that you guys are spending your time with me. And please follow along to the channel if you're enjoying it. Please leave a like if you're here. It just really helps to have other people get filtered into the channel and the algorithm. It creates the bigger community and also just helps the channel grow and shows some support and motivates me to keep going. And so if you guys feel inclined to, throw it a like and follow along and join the Discord. I love talking to you guys. This makes it so much better. Okay. Um, let's take a stab at 7, 2, right? Okay. Now let's see here. All right. Describe a good algorithm for concatenating two singly linked lists L and M, given only references to the first node of each list in a single list L that contains all nodes of L followed by nodes of M. Okay, so now should we write the algorithm or should we describe it? I think it would be better if we write it. Um, so this one we need to traverse L all the way until we find the until we find the final value or the tail, and then we need to set the tail's next value equal to the singly linked list M header, right? So let's define combine singly linked lists, right? It's going to take in some singly linked list L, or take in some singly linked in list L and M. Okay, so we first need to establish some base cases. If so do we want to first recursively travel down L? Okay. So given some L, we need to say if L head is equal to none, or L dot head dot next is equal to none, return none, right? So if the L linked list head is none, or the L's head next value is none, we're going to return none, right? If we're going to set node is equal to L dot head, or sorry, we'll say our base case is going to be if L dot, in the previous problem our base case was what? If next node is none, right? So no, so this is not our base case here. This is our base case. This one would be this is our edge case. This one is our base case. So let's take this down. Say here, if the L head dot next is equal to none, meaning that this is the tail, we are going to return L dot head dot next is equal to, or no, we're going to set L dot head dot next we're going to, if L dot head dot next is equal to none, we're going to set the next value equal to the M dot head, right? Perfect. And then what, just return out of this, return nothing. So then we'll say the else case is Mamet, I appreciate you. You are doing a great job. Excellent motivation. Awesome. I appreciate you guys are enjoying this. I really wanted to, provide a sense of safety here and just general enjoyment of programming. So if that's what you guys are enjoying, I appreciate that. Thank you so much. Okay, so if then we need to recursively call a return for on l.head.next, right? Return combine singly linked lists for l.head.next, right? Okay, so what's going on here? We're given some linked list L and M. If the header of the linked list L is equal to a value of none, then we're going to return none, meaning that this linked list is empty. Right? Another edge case would be if l.head is equal to none and m.head right? We're going to return if there is values in the L header, if there is values in L and m.head is equal to none, we're going to return L, right? Return just the value of L. So this one says if there are no values, nodes in the linked list, return none. This one says if there are values, if there are nodes in linked list L, in L, and none in M, return L, right? This one says else our base case, so these are edge cases, edge case, this is an edge case as well, right? So our base case here is if the l.head.next is equal to none, meaning that we are at our tail, then now with the linked list, you guys, can we access directly the l.tail? Or no, we have to traverse down from the head to the tail. So if the head next is equal to none, we've met our base case. We're going to set the head.next equal to the m value dot head to continue concatenate these two linked lists together. And we're going to return and we're going to just return from there. So is this done? We're going to combine, call this to the next value, on head dot next. But this is calling in some node of L. Giving only references to the first node of each list. Okay, so this is a reference L node head, and this is M node head, right? So if L so this is L node head is equal to none, we're returning, this is L node head and M node head equal to none, return L return just nothing. If L node head dot next is equal to none, we're going to take L head L node head dot next and set it equal to M node head, right? And return from there. Else we're going to call L node head M node head. Or call this for dot next here. Mahan says, we went for a little celebration for New Year's, and you're still grinding. Yeah. Mahan might be a little bit under the influence here. He had a appreciate you coming in. Okay. So how does this look? Okay, let's map this out on our recursion trace here. So we have some linked list L, which houses node A, B, and C, right? Right. We have some list M, which houses D, E, and F. We are given L node head and M node head as our parameters. If the L node head is equal to none, so if we don't have anything in, we're going to turn none. If the L node head, if we have L nodes, and M node head is equal to none, we're going to return, just return, meaning that we have the value of the return to L's. Return none, right? This would return none as well, right? Except if we're going to then say, okay, if the node head next, so the one that was provided, so A was provided initially for L, if the next value is equal to none, we're going to then, right, which is not the case, so we're going to continually trace down until we get to C. Okay, the next value is equal to none, so now we're going to set this value none equal to D here and continue on. Nothing wrong with a little bit of whisking off program. Happy New Year, Technically Data. Appreciate you coming in and saying hello. Welcome, welcome. How you doing? Appreciate you guys coming here. We've been streaming for over 3 hours so far. Appreciate you guys joining me. I'm feeling really good. Feeling a lot better about linked lists, at least singly linked lists, than I did before with these practice problems and with your guys' help. So I really appreciate you guys helping me out here. So I think that this is okay. What do you guys think? Let's go ahead and ask the almighty orb here. I am solving this problem. Let me show you what I have so far. Okay, you're on the right track with your recursive approach. However, there are a couple of adjustments to make. Edge cases. If L node head is equal to none, is correct for an empty list L. The second check, if L node head and M node head is equal to none, is not quite right. It should check if M node head is none while keeping L node head valid. This condition can be written. Okay, so we don't need this check here. So we can just check if M node. Right, is equal to none. Similarly, you can check, let me say, don't show code. Okay, so this one said, similarly, if you check L node head next equals none, you need to link if you need to so this one says if L node head. So this wants me to return L node head. Right here, rather. Recursively call this traverse the last node of L. Recursively call this and return L node head at the end. So why are we recursively calling this with not on the return though? Mahan says, can't you just set next of L head to tail M and say head of M is head of new singly linked list and tail of L? I'm not sure what yours. I'm not sure. I'm not following you, Mahan. Can't you just set next of L head to tail of M? So why does the almighty orb call why does it call why are you not calling return on the CSLL function? In a singly linked list, you typically not return values in the recursive functions, especially when you modify the next pointers and want to return the header of the list after the overall operation. In the recursive function I explained earlier, I didn't show return statements for every recursive step. Here's why. At the base case, so we don't need to return the final value. We don't want to return what gets spat out here. We just want to return at the very end L node head, right? Because this is getting returned back for all of these, which in theory would just return here. Right? This still does this statement not work? The statement return does work, but it requires a little more understanding of how recursion and return values are being handled. In recursive function, the line is invoking the function again in the next line of node, which means the function will keep calling itself until it reaches the last node, but it doesn't update the next pointer of the node along the way until your current implementation. To make it work properly, you need to reach the last node of L. You should set the last node, return the L node head. Why your head here never gets changed. So this value gets returned to here. Which in a sense gets returned again for each call backwards. So is this wrong? Your current code has a small issue. How do you actually implement singly list list? Is the head if the is the head automatically finds the head, or should you set it? So this one states that the given parameter is the first node of each list. So it's just inferred here that each node provided is a singly linked list. Now we do have some edge cases to check if it is, but that's what we're inferring here, is that these are the start of singly linked lists or heads provided. So this then says, so def combine singly linked lists, L node head, M node head. If L node head is equal to is none, return that. If M node head is none, return that. Oh, we want to return M node head. And then we want to return L node head here, right? If L node head dot next is none, L node head next is equal to M node head, return L node head, return these. Okay, cool. I think that works appropriately. So now let's take in this node class, bring it in, put this up here. We'll create a few nodes like so. Okay, we'll create a few more nodes. M1 is equal to node 6. M2 is equal to node 7. And M3 is equal to node 8. Okay, we need to set the next values for these here. So m1 dot next is equal to m2, and we say m2 dot next is equal to m3. Now we're going to call our function combine linked lists for n1 and m2, or m1, sorry. Now we want to return what do we want to return to show that this was successful? So I run this. I'm not getting anything. We need to call a print here, right? If we call a print, that'll give us node 5. Which returns the last node in our list. When you add to the head, your head changes to new one or not. You need to do it manually. So this is going to return so we don't want to do this here. We want to return L node head here, right? So this should give us N1 now, node 1, perfect, like that. Now, how can we determine that M was successfully added on here? Can we call like dot next times 5? Like do it 5 times? No, that doesn't have, we don't have that implemented for the multiple function. Shouldn't we traverse from the first list to the last node to connect the first node head of the second list? Yeah, I think that's what we're doing, right? So we are going to continually traverse down by calling next on the L node head. Once we reach that the L node head next is none, which is our base case, we set the next value to the M node head, and we return L node head here. So now if we call a dot next on this, that'll give us 2, right? Now if I call another dot next on here, that should give us the 3. Okay. Now if I call another dot next on here, that should give us the 4. Now if I call another next, that gives us the 5. Now if I call it one more time, we should get the 6 here. If we don't get the 6, we have it wrong. Boom. Cool. Awesome. So we are appropriately appending those nodes, right? Right, and that should be 7. Okay, so our 7 isn't appropriately working. So we're getting the 6, but it's not continuing downward, even though that these are already established as the next values for those nodes. What do you guys think? So, right, we have 6 calls here, so we're getting this node 6 here, which is the first start in our M, but we are not appropriately keeping our 7th and 8th values here. We're assigning the next to the node head. Shouldn't you get 8 after 1? No. All we're doing is we have 2 references to the first values, right? So M1 is node 6 and N1 is node 1. We are trying to just concatenate these 2 together. So it should be just 1, 2, 3, 4, 5, 6, 7, 8, right? We're trying to set the tail of our L, or our node 5, to the pointer to point at the start of M. So we are setting the next value to node head. Head of one to the tail of the other. Yeah, that's exactly what we're doing. We're putting the head of M to the tail of L. Describe a good algorithm for concatenating 2 singly linked lists L and M given only references to the first node of each list into a single list L prime that contains all nodes of L followed by all nodes of M. So it should be all nodes of L 1 through 5 followed by all nodes of M 6 through 8. So we are successfully getting the right? We're successfully getting the concatenation of the M node head to the last value right here, node 6, but we're not keeping these next values here. So the heads are just each element as we go down, right? Each one becomes the new head at this point for each of these nodes. So we're just supposed to concatenate these 2 lists together, making the M linked list precede or follow the L linked list. So this should not be inserted anywhere in between. It needs to follow at the end. L list followed by M list. We're setting the trail or the tail pointer of the L list to the start of the M list, so it will continue from there. But Yeah, Joseph T. George, recursion is confusing for me. Yeah, definitely. I feel that one. Recursion is definitely a trickier one. I'm still getting practice with it for sure. So we'll say I am setting the tail of L to point to the head of M, but it does not continue with values in M. Tail dot. So this is what I have. Could start, but there are a few issues. Recursion logic. The recursive call, you're not properly connecting the last node of L to the head of M. The recursive call should update the next pointer of the last node in L, the node that comes just before none, to point at M head, returning incorrect node. In the base case, you only need to update the next pointer of L node head, but don't return the updated list of the recursive call. Solution. Basic idea. The traverse to the end of L and set the next pointer to the head of M. Return the head of L since it now represents the concatenated list. Oh, so they have a while loop. They say while current dot next. Hmm. Okay, so if you connect L to M, right, you get 1 through 8. So you need to do 1 through 5 to M1. Yeah, exactly. Or L5 to M1. And you only have L5 and M3. No, so we're not um, getting past the 6 here, right? We're successfully putting the M node head to the L node head dot next as we recursively go down, but we're not keeping these set next here, right? We're setting the what if I say M2 is equal to M1 dot next? What if I invert these? Call next here. And then say what if I flip these? Doesn't like that. No. None associated with the next. M2 dot next is none. It's the tail. You can just set it like, no, okay. So it'd have to be the other way around, like we had it before. All right. Hey, Matter, I appreciate you coming in. Happy New Year to you. Welcome, welcome. I hope you're having a great day. We still got 1 hour left in the year 2024 for me. It's currently 11:08 p.m. I'll probably wrap up the stream here shortly and just kind of enjoy the last little bit of the new year with my girlfriend. But I'm trying to solve this one problem before we finish here, and I just am stuck. And we might have to pick this back up tomorrow. I do have tomorrow off of work, you guys. Yes, Mahan, you're all good. No worries. I figured that we were just having a little bit of a disconnect here. No worries. Yeah, I think you're figuring it out here with me. So I don't know why though. Maybe return the function. Okay, let's try. Let's return the function. Let's return the function. Okay, we get node 5, which returns the node head, right, that was associated with this next call. So what if I call dot next here? None. Invalid syntax. Oh, we have a dot there still. Node 6. Now what if I do another dot next? Node 7. Okay. And dot next here. This should give us node 8. Perfect. Okay, so that is working. So then this will return. Okay, gotcha. So now it works appropriately. But it's returning the 5th value, right? We don't want it to return the 5th value where it starts. We want it to return. What do you mean bend to? I'm sorry, hold on. So we're returning the head, but this returns the value that is being, appended here, or that is being set here at this current iteration. So it's returning this tail. We want it to return the start. Hmm. So this works, but we're returning node 5 here, which is the Yes, exactly. That's what we're doing here, Mahan. So we're traversing L down, and we get to our base case of node 5, which is the last node or our tail node in our L linked list. We then set, once we realize that we're at our tail, we set the M node head that's provided equal to the L node head dot next, and we return. What if we just return no value here? None. None is returned. So we do need to return a value. I have two edge cases because this first edge case determines if there is no L, right? Well, then we return the M list. And if there is no M, we return the L list. That's why we have two edge cases. So if either of these are none, we return the other one. I think you can just traverse with no return and output the head. So rather than don't return any value here, do that. No, that causes a recursion depth error. So we have returning this. Yeah, Madur. That's what ChatGPT was suggesting here. It said, whoops, sorry. It said that we could use a while loop to continually go down and next until and then return L node head. Exactly like what you said. But if I wanted to keep it with recursion, sticking with recursion, my function is correct, but it is returning the tail of the length of L. How can I instead return the head or start of the original L? You're correct in your approach of using recursion, but as you pointed out, your function currently returns the tail or last node of L rather than the head of L. The key here is to ensure that while you're recursively traversing L to find the tail, you still need to return head after the recursion is complete. In your current implementation, the function returns the result, which is the last node. To fix this, we need to make sure that the head of the L is returned after the entire recursive process finishes. Okay, so they're doing it the other way. So they call this, and they return L node head here. We get node 1. But if I add in dot next here, this is for the 2, 3, 4, 5, 6, 7, we get none. So this approach does only append, or it only sets the tail of L to start of M, but does not keep the rest of M. You're correct, and I see where the confusion lies. The problem in your current recursive approach is that you're only updating the next pointer of the last node in L to point to M, but the recursion did not properly link the full list M to L. Specifically, you're not ensuring that the rest of M gets connected. The key here is to correctly handle the base case in recursion. In the recursion approach, while traversing L, you need to ensure that the tail of L is connected to the head of M. The entire list of M is preserved. L node head next is none. L node head x is equal to L node. Return L node head. Combine L node head dot next for L node. So this is what I'm setting this to. So they have this while current. Oh, but they print. This is just printing. Okay, hold on. Put return but with nothing. Remember, like we did a couple of days ago. Once you unfold the recursion, L node head will be N1. You got to traverse back. It makes sense for the head to be at 5, since by the time you append the next list, the head set is at 5. No. You need to save the head of the list you're traversing somewhere and return after that completion. Okay, so we need to save the head somewhere in this list and return that value. So we have to save above here, above our edge case here, our base case, we'll say head is equal to L node head. Let's come down here. Return this function. L node head gets placed into here, which gets returned. So we save the head is equal to this. We call this recursion and then return head, like so. Okay, there we get node 1. But if I call head dot next, call this 7 times, we get none. So if we return here, so this successfully will return the last place of our list here. What did you change? I didn't actually change the logic. I just provided a complete example. So I'm going to return nothing, right? I'm going to call this function on this. I'm going to say while current dot next, while you concurrently current dot next, we're going to say, what did they say? While there is current, print current dot data. Wow, current dot data. So this is going to be new L linked list is equal to this. We're going to say So the new linked list is equal to that combined. And then we say while new linked list, we're going to say print new linked list. What does that do? Oh, come on, get over there. That doesn't do anything. Because it's not returning any values here. So the only thing, Mahan, is we can't really just kind of edit the parameters because the problem does say that we specifically only given references to the first node of each list. We could say like L node head 2 and return L node head 2, like so, right? That would be an easy kind of escape here, right? Like so. But I don't want to add additional parameters because I don't think the problem really wants us to. So if we return nothing here, what happens if we call a print on this? None object. Because nothing is returned here. So if I take this guy, put it here, current.data. I don't have a data attribute. Oh yeah, I do. Self.data. So if I do this, this gives me 5, 6, 7, 8. Node 6, 7, node next goes into. It won't print because the current is none. Yeah. We'll make a copy of the head before the function. Yeah, Mahan, we'd have to use a while loop. With the recursion, we're stopping on this value and we're performing an action and we're not actually, recursing back up through our function or back through our linked list and providing that start most value. We're stopping at the tail, appending, and then stopping there. So there is no back recursion taking place in this function. make a copy of the head before the function. So if I combine these and I just call a print on N1, that'll print node 1, right? Now if I call while values in new, while there's values in the new linked list, right, we're not returning anything. We're just going to return while there's values in the new linked list. Print oh my gosh. Do a while loop starting from node 1 to print the next values until it's null to see if it's connected after running the combine function. Yeah, so while there are values in new linked list, well, new linked list is going to return none. None is returned here. So we're going to combine these together. And then call for in range we need to do this 8 times. So 8, we're going to print n1 dot next. So this is going to miss the first value of 1 though. We get node 2 every time. So we're printing n1 next the whole time. If we physically take this guy here, put it in here, and then take this and set it equal to this, right? We're not getting it. Because we're having none is returned here. So nothing is being returned as current. I'm just trying to, I know we can solve it easily with the while loop, right? But I already got this far with the recursion, so I'm kind of in like a sunk cost fallacy right now where I'm like, well, I'm already this far, I kind of want to solve it with recursion. We've already put in this much work with recursion, so I feel like I want to solve it with recursion, but it's causing more difficulty than it's worth here. This is returning L node head, combining and then we need to return L node head here and then just call this. So that'll do it like that, boom. Yeah. So you return here, this gets returned, and then afterwards you finally return just the initial value at the very start, and then we can while iterate through and do them. Right. So we're just going to return the initial head no matter what. Yeah. Cool. Appreciate you guys' help with this. I know I was kind of just wanting to work through it here via recursion because we already got so far here. But yeah, thank you guys so much for helping me out here. So I guess you can return none here. You don't really need to do anything here. It would still give you the values. No, you do need to return a value here. Right, so this will return the point at which the header, the tail, right? This will return the tail back to this function. And then in the end, right, we're going to just, rather than returning the call back to the tail of the L, we're going to just return the very start of the L and bypass that. This returns number 5, node 5, the one that's specifically handled here, right? Okay. So what's going on here is, right, we have two edge cases here where if the L node is a none value, we just give the M node. And if the M node is none value, we give the L node, right? If the L node head dot next is none, we've reached our base case, meaning that we're at the L node, the L's tail. And then, right, which means then we need to set the next value equal to the M node head. We're going to return this value here, and which gets replaced into here, this recursion. Now, this node 5 is what's being returned here, and recursed back, but we don't want to return node 5. We want to override that and return just L node head at the very end of our recursion process, which will be just this value of node 1. Can you try returning line 28 and returning none on line 26? Yeah, so if I return none here, and I return here rather than this, what do we get? Yeah, none, right? Because we're returning none for this value and returning none here as well. And so our none value gets stuck here and none as well there. So while none, well, we can't do that. Oh, still return line 30. Well, I can't return line 30 here if I return on line 28. Right. So if you return none, none gets filled in for this bad boy, which gets returned and set to this. So if we print, right, if we go like this and do, oops. Instead, if we just printed new L, right, we'd get none. Exactly. Oh yeah, then that's me being dumb. No reason to do N1, M2, M1 when you already have it. LOL. Yeah. No worries. I appreciate Mahan. No, I really appreciate you being here, Mahan, and walking me through this. Same with you, Travis. I really appreciate you joining me here. Madur, thank you. Ben, too. Thank you guys so much for helping me out with these problems. All right, so we've successfully done this one. There we go. Ooh. What the heck is going on here? What's going on? Why is it being weird? There we go. Cool. All right, that's the answer to this one. Why return L node head and store the new L? Why return the L node head and store the new L? Well, this is returning, right, the tail of L back to here, but override the return of L tail with the start of L head. Right? Cool. All right, so this is the answer to this one. We did it. We could have done it really easily with a while loop. So what happens if I return none here, but I do return this value? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it does work. So we can return none here. So we can just return blankly here. And then do that. Yeah, perfect. So we don't even need to return the tail. We can just by default turn the head because we've done this concatenation and we can be done. We don't need to do anything. Awesome. Just like that. I like that better. What do you guys think? Do you like that better? This is what I got so far. Oh yeah, I wanted to see this one. When I said line 28, line 26 thing. Got you. Perfect. Yeah, that's exactly, we didn't need this value at all. We didn't need to override it, right? If we're going to override it, we didn't even need to return it. We just needed to recursively call this and get down to our base case. Once we reach our base case, we perform some sort of action and then we're done. So we just need to actually return our initial head and be done from there. Hey, GC Zonk, I appreciate you coming in. Yeah, I'm a beginner programmer. I've only been teaching myself for about 6 months so far. I started off at the very beginning of this book, and at the chapters 1 and 2 give you review and introduction into a review over Python's object-oriented programming and some methods and things like that, and then you dive deep into data structures and algorithms. So I'm a beginner and still am, and I was able to traverse through this book over the past couple of weeks and I'm picking up these things. So yeah, this can definitely be applied to beginners. I'm a beginner. I'm teaching myself for the first time. I really appreciate how you guys are you're joining me here. I'm going from watching how to code to how to fix forward head posture in 2025. You calling me out here? You calling me out here, man? Why are you calling me out, John? Yeah, I need to. New Year's resolution is to fix my T-Rex posture here, right? Gotta lean back, lean back. John's calling me out. All right. Cool. So we've solved this problem. All right, you guys. I've been streaming for over 4 hours today. Oh my gosh. I need to my girlfriend. I need to spend some time with my girlfriend and my dog. Today I need to show them some love and attention here. Been streaming for far too long here. Michael, do you plan to do database stuff on your project? I'm not sure. I would love to maybe incorporate something if needed. If you guys have any suggestions of how I can incorporate stuff, please tell me. I really appreciate you. Appreciate you helping me with that. But I'm not sure where we could implement something into the small business manager for a data structure. Um, we don't have anything like a queue, right? I mean, or a double-ended queue or a stack because items can be removed just at any point. So, but I'm currently accessing my items via item number as the key in dictionary. So everything is running in constant time as it is right now. So it is pretty efficient for accessing items that way. Um, LS Dominguez, good morning, everyone, and Happy New Year, by the way. Yes, Happy New Year to you. If you're in 2025 in the future, Happy New Year to you. It's 11:45 p.m. for me right now. We've been streaming for over 4 hours and 15 minutes so far. Should I just stay on for the last 15 minutes or and be here for the new year, or I might call it here in just a second to spend some time with my girlfriend and my dog going into the new year and um, just chilling out for the rest of the evening. But I don't work tomorrow on the New Year, so I'll be back on my stream tomorrow where we'll go over all of some more DSA and keep going here on these practice problems. Madura, I appreciate you trying recursive approach, but just FYI, we should try to use iterative when possible to avoid recursive stack storage. Oh, awesome. Okay, so yeah, I wanted to try the recursive approaches because we were kind of in a sunk cost position where we had been working on this for about a half an hour, 45 minutes. And so I was like, dang, if I've been going this far, I want to finish the recursion. But yes, tomorrow we're going to take a jump and look at maybe solving some of these in iterations. And so we'll need to do that as well. So like, while whatever, right? Um, Hey Abakar, thanks so much for coming in. I appreciate you joining me. Yeah, for those that do know but don't know and that are new, before I go ahead and sign off for the live, we've been streaming for over 4 hours and 15 minutes so far. I stream every day, or at least I try to after my 9 to 5 job. I graduated back in 2021 as a with a human bachelor of science in human biology and a minor in chemistry. I work as a formulation chemist. I got a job right out of college and back in 2021, beginning of 2022, as a formulation chemist for a biotech company. I'm currently a mid-level scientist too, as my title in that position. I've been teaching myself Python for the past, about 6 months. I started with Harvard CS50P and transitioned out of that course after I completed it. I created this channel. And then for the past 3 months since I've been having this channel after I completed Harvard CS50P, I've been really grinding and I've really caught a fire and a passion for learning this. So if this is something that you're interested in and enjoy this kind of format on the stream of me reading through various online resources, solving practice problems, working on live projects, please follow along. I really appreciate you guys joining me. So far, I have a Discord linked below in the description of this video and all of my streams where I've created a online community and provide all of my study resources, kind of like a roadmap. If you guys are interested in getting access to all my study resources from the books I read to even other subscribers and followers of the channel who are currently CS majors have also supplied their own current study resources that they're using. So if that sounds like something you're interested in, please join the Discord. I'm also going to be starting in 2025, come tomorrow. The Harvard CS50X is going to be relaunching their course over their curriculum, and the yeah, so Harvard CS50X is going to be revamping their program tomorrow, so we're going to be starting that up and completing it, and we're doing a live watch along and complete of the course on the stream. So please follow along if you're interested in doing and completing that course with me. Um, so in the beginning of my streams, we work on live learning, going over various. So right now we're reading data structures and algorithms in Python, where we are currently just finished chapter 7 on linked lists and are applying some reinforcement problems to solidify our learning. And then usually in the back half of my streams, or at least I try to, we implement the learning that we're doing into live projects. So currently I'm writing from scratch a small business manager project, which has this data structure class here. And I have a script written here where it performs various kind of menu functions where I'll do a quick demo here where we can enter into the program, access different inventory items, add items to inventory, edit those items, transact those items, and view them. We can also go back to the main menu and go to the transactions menu, do an item search for a specific item, look up the item, gain access to that item, and then convert these items into a for sale item and a sold item. We can update parameters accordingly, giving them a date listed, a listing price, a date sold, and a sold price. Manage that data, calculate, cost versus revenues, and display, in various reporting mechanisms to the small business owner that, hey, over the course of X amount of time, throughout whatever filtering mechanisms that we implement, we can generate them like income statements, revenue statements, cost statements, expense reports, all that kind of general small business needs. So this is a really cool program that we've been writing live from scratch that could be very useful to a bunch of small business owners like myself. So um, I'm just kind of modeling this after something that I would use for my small business that I own. With my girlfriend, we sell and manage like vintage clothing online. It's kind of a passion of hers, and so yeah, this would be something that would really be applicable into managing that inventory. And I've been having to do this all by hand, through Excel and various other resources. So by having a program just automatically convert these transactions and provide reports would be really cool. And so in the back half of my streams, we focus on implementing our learning into actual projects to solidify and just prove that we are learning these things. So this is really cool that we're working on this. But today we didn't get time to work on this because we were really grinding away at the linked list at the end of chapter 7 here. We got some chats here. Really quickly here. Everybody's telling me to go spend New Year's with my girlfriend. Yeah, I need to. I am just kind of wrapping up here, you guys. Appreciate you guys joining me. I'm studying with English books. They are better than Spanish books. Can you write me a link or name? I don't understand English very well. Um, yeah, go ahead and join the description below if you want access to all of the books I'm reading that are in English. So I provide all of these books that I'm reading in the description in the Discord below. Mahan says, you have data stored on network and the business people can access them on any device. Maybe they can have multiple PCs. The file is only for one PC. Okay, yeah. Joseph T. George says, this may sound like a stupid question. What if you define the combined singly linked list method into a class called singly linked list and call the method? Do we need to return the L node head? Yeah, if you had your own class, you could probably just return that class, right? And it would probably handle those things accordingly. We just created these node connections manually rather than creating a singly linked list class, right? Yeah. Abakar, thanks so much for coming in. He says, nice, awesome. Any advice, attacks, directly projects, cover the things you missed, you'll learn way faster. Yeah, exactly. Panva says it's 11:47. Still got New Year's for the West Coast guys. Yes, exactly. I'm 11:51 here. I'm in the same boat as you. Welcome. Yeah, exactly. Okay, cool. Yeah, so I currently run a Bakar. I currently run that small business manager in the CLI interface. But my goal is after I get a working prototype of a version 1, I would like to convert it into a GUI or a graphic user interface for users to be able to have more of a desktop executable application. I think would be cool. Or maybe when we're doing the CS50X course come in 2025 tomorrow, we can maybe implement it into more like a full stack kind of through the internet, like a Google interface would be cool. What time is it over here? It is 11:52 for me, you guys. All right. Yeah, it's still 2024. I'm in the past. I'm in the past here, which is really kind of crazy to think about this. Some of you guys are in a whole new year, and I'm still in the past here, which is kind of wild. All right. Thank you guys so much for joining me today. I'm going to call it here. It's just before the new year. I really appreciate you guys joining me. We streamed for 4 hours and 25 minutes today. I'm gonna go spend the New Year's with the last remaining time of New Year's and spend it with my girlfriend and my dog and my aunt and my cat, just kind of hang out. I will be back tomorrow. I don't have work tomorrow for the new year. I really appreciate you guys being here again. Please like this stream if you enjoyed spending time with me and enjoy the content. It really helps to motivate me to keep coming back as well as to bring in other people to see the stream. I really appreciate that. The algorithm's been picking us up, and a lot of new people have been joining. Join the Discord so we can talk offline and gain access to all the resources. Please follow along to the channel so I can connect with you guys again in my future streams. We'll be back tomorrow, and I'll do announcements in the Discord about when I'm going live. But I'll see you guys then. Thanks so much for joining me today. Happy New Year. Be safe out there. Don't party too hard. You guys are great. Thank you so much, guys. See you tomorrow.